All right, so we continue on part 2 of the geometrical optics lecture. Again, geometrical optics is covered in chapters 25 and 26 of Cutnell and Johnson. This is the last picture where I ended, and then again, we're talking about what's called total internal reflection. Again, so remind ourselves, again, total internal reflection. So I imagine a point source of light at some sort of a depth. There's an air glass interface. So somehow I have a point source of light down here, or you can think of this as being air water. It doesn't really matter. The important thing is on one side of the interface is a material that has index of refraction N2. On the other side of the interface is a material with index of refraction N1. And for this process, what we call this phenomena of total internal reflection to actually work, N2, the medium which you'd be going in, which you'd be actually transmitting into, has got to have a lower index of refraction than the material that you're in right now, N1. So the material in which the incident ray, the material in which the transmitted ray would go into, must have an index of refraction lower than the material in which the incident ray exists for this to work. All right. So you notice what happens is you have this point source, and of course the point source is isotropically emanating rays everywhere, and so here's a ray that you see at point B. And again, when you're talking about an index of refraction where the material in which the light's being transmitted is less than the material in which the light is incident, then the ray will bend away from the normal. Now, we've been, again, in the past, we've been dealing with materials where we go, let's say, air into glass, where the index of refraction N1 is less than N2. That way, the light's always bending toward the normal. In this particular case, light always bends away from the normal. And so there's an example of point B. If I go further out and consider a larger angle of incidence, I'll have a larger angle of refraction, or angle of transmission, angle of theta t. And at some point, I'll get to a special critical incident angle. We call it theta critical. In this particular case, this would be theta critical. This incident angle is such that the refracted angle will be 90 degrees. At this particular critical point, no light whatsoever will be transmitted to medium 2. Absolutely none, no light. All of it will be totally internally reflected with no losses whatsoever. And if you consider larger incident angles, the light is just going to continue being totally internally reflected. All right, and so this is really a three-dimensional picture. You can think of a point source of light. You can think of this being really the radius of a circle. Where you have a circle of this particular radius and all the way around in all directions on that, in a circle of that radius going from A to D, you'd have light that would be transmitting out, and any other light that would be at an incident angle in any direction greater than theta sub c, or greater than or equal to theta sub c, would be totally internally reflected. You'd have complete extinguishing of light for any other larger angle of incidence. Now, this phenomena is extremely important to our technology. All right, and so why is it important? Well, let me give you a nice, cool example first of all and then I'll start talking about application. So I did this in the lab myself, and I took optics. I actually took a class entirely on optics. Full-blown Maxwell's equations and everything else. And this is a class for a junior level, senior level physics major at the undergraduate level. And let me share my screen. One of the cool things, they did a lot of really neat experiments in that class. But I thought this is fairly simple, but very cool indeed. So you take a look at this picture. This is a picture of basically a tub of water, and we're aiming a laser such that there's a hole in the side of this tub of water. So the hole is going to allow a stream of water to leave the side of the tub, and the stream of water will descend in a parabolic arc because of gravity. So all the water droplets, all the droplets of water that compose this particular stream will all be falling due to gravity. They'll all be undergoing a parabolic arc. But what's interesting is if you shine this laser, very intense beam of light, and you aim it at that hole, the light, as you see, the light gets trapped in that stream of water. It cannot escape. It's continuously being totally internally reflected within that water, and the water is lit up all the way down its path, all the way down to the ground. The water is lit up. It's constantly being totally internally reflected. None of the light escapes until there is no more stream. This is how fiber optics works. This is how a colonal fibroscope works. So a medical doctor, for instance, wants to look inside your colon, for instance. Now, what does the doctor do? Well, a doctor will have kind of a snaky material device that's made out of basically a fiber optic cable, long fiber optic device that can snake around, it can bend, and on the end of it is a TV camera and a light. And the doctor can take an image of something inside of your body, inside of your colon, for instance, looking for, let's say, a possibly cancerous polyps. And that image can be transmitted back along the fiber back to the computer processing system in order to be able to give an image to the doctor. Exactly the same phenomena as I'm showing you here with this laser in a tub of water. You can actually transmit an image right back to the and the doctor can look remotely at the inside of your body without actually having to go there and make an incision. All right, that's called a colonal fibroscope. So again, I'll just kind of write this down we have some people in this course that are future medical doctors. So this is how that works. Again, it's all based on total internal reflection. So what we call the colonal fibroscope. The colonal fibroscope operates on total internal reflection. So I'm going to show you another picture here. Actually, another important is in communication systems, fiber optics. Fiber optics also depends on total internal reflection. We can extend fiber cables. Literally at this point, they're all across the United States. They're all across the oceans. And we can get communications at light speed and have no losses. There are no losses in total internal reflection. And these devices are set up such that you have an internal core and it's surrounded by what's called cladding. The cladding is these material at a higher index of refraction that allows the light to be internally reflected at really at large incident angles. So let's show you a picture here real quick from the book. Not the best picture I've ever seen, but better than what I can draw. Let's put it that way. So share my screen. Here is a close-up of a fiber optic cable. Now, inside, you have index N1 is a core. That is your core, made out of some sort of material that has an index of refraction N1. On the outside of the core is a covering, if you will. It's called a cladding, C-L-A-D-D-I-N-G. And has an index of refraction N2. Now, the important thing is N2 has to be less than N1, just like in our example, because the light has to be totally internally reflected. And with this light being propagated in this way, you can get a signal going all the way across wherever you want at the speed of light, or the speed of light in, that would be in this material N1, V is C divided by N, remember? And you would have the signal entirely confined in this cable. And you can snake it around however you like. If you want to make 90-degree angles, you want to do loop-de-loops or whatever it is that you need to do with this cable, you can do it. And that light will continue to follow it. And in fact, the index of refraction choices will be such that you'll be able to handle large angles of incidence, which means that there won't be much difference between N1 and N2. You have a large angle of incidence that'll actually be able to be handled, so you can actually snake this cable around any way you like. So again, this is the same phenomena that I just showed you with the tub of water holding the laser beam. Again, the colonal fiberscope used by medical doctors operates on this very principle, as well as fiber optics. A lot of people, I have FiOS at my house. It's internet that's done via fiber optic cables. So my internet, the very internet that I'm talking to you on right now, is via fiber optics. All right, and so again, very, very important concept. Let's work a couple problems out with total internal reflection. I'm going to work on problem OpenStax 25.21. Okay, that says, A, at the end of example 25.4, restate some of this. At the end of example 25.4, it was stated that the critical angle for light going from diamond to air was 24.4 degrees. Verify this. Okay, and then B says, what is the critical angle for light going from zircon to air? All right. So part 25 and 21 OpenStax, part A says at the end of example 25.4, it was stated that the critical angle for light going from diamond to air was 24.4 degrees. Verify this. B, What is the critical angle for light going from zircon to air? Okay, so again, we're going to do a critical angle calculation. Critical angle means total internal reflection. All right. So what do you do again? So again, remember what total internal reflection was. We have N1. Again, N1 must be. So you have light coming in. Remind ourselves what this means again. Light's coming in, and there is a critical angle. You are at N1 below the medium and N2 above the medium, and of course N2 must be less than N1 for this to happen. All right, and so we don't have a transmitted ray. The ray at this critical angle is literally along the surface. No transmitted ray here. All right. So so what do you get? Well, this is a 90-degree angle with respect to the normal in the transmitted region. So you use Snell's law. Snell's law is another way of saying the law of refraction. Snell's law says N1, now sine theta incident or theta sub I. Well, theta sub I is going to be the critical angle in this case. Will be N2, and then of course the transmitted angle for the critical angle will be 90 degrees. Now we know the sine of 90 degrees is 1 in this particular case. And so what we get is that N1 sine of theta critical is N2, and sine of theta critical will simply be N2 over N1. And how do you get theta critical? You take the inverse sine of both sides, or the arc sine. So theta critical is the inverse sine of N2 over N1. All right, so that is how you find the critical angle. All right, so using that formula, we know that we're talking about N1 being diamond, N2, the material there is air. Diamond going into air. Well, we do some lookups here. Well, we know, of course, that, N1 for air, we said this multiple times already, N1 is 1.000293. N2 for diamond, you look that up, you'll find that that's equal to 2.419. That's one of the highest indices of refraction that we know. That's what gives diamond its sparkle. Put this in, theta critical is just the inverse sine. N2 is 2.419. Actually, I got this backwards. This is backwards. N1 is diamond, N2 is air. Sorry about that. N1 is diamond. That's the 2.419. N2 is air. That's 1.000293. Just a little bit more to the back. All right. Put this in. 1.000293 divided by 2.419. And you do this, you find out that theta critical is going to be 24.4 degrees, which is exactly what that example said and what you were asked to verify. What about zircon? So part B now is pretty much about the same math. And now instead of diamond, now you have zircon. You guys have heard of zirconium, fake diamonds. One way to find out if your diamond's real or not is to see what its critical angle is. If you really have a diamond, you better have 2.419. Zircon, on the other hand, is 1.923. It may look like diamond, but it's not diamond. All right, so a lot of times people make fake diamonds out of zircon, or they call them zirconium, right? And so what do? Well, you did the exact same math, except this becomes 1.923 instead of 2.419. And you'll find out if you do that math, the critical angle is not 24.4 degrees, but it is 31.3 degrees. So if you have a quote unquote diamond that's giving you a critical angle of 31.3 degrees, you don't have a diamond. You have something else. You probably have cubic zirconium, as they call it, cubic zirconium, whatever it's a form of zircon. All right, and so again, that's one way of seeing if you're if the person passing you a quote unquote diamond is a real diamond. Okay, Opus X 25.22. Okay, that says an optical fiber was flint glass clad was flint glass clad with crown glass. Sorry. All right. What is the critical angle? Hey, what does this mean? Well, let me look at, remember that picture I showed you, the fiber optic? Let me look at it edge on. Let me imagine one of these fiber optics I'm looking at edge on. All right. What does that mean? Well, it means inside of this is flint, and on the outside is crown. Again, this picture's not drawn to, this picture is in no way drawn to scale. I'm just trying to put words in here. So on the inside, the core of this is going to be flint. On the outside will be crown. That's the cladding. Crown glass, right? And so essentially we have two different indices of refraction. We have to have the N1, we have to have N2 less than N1. So this is flint, which would be N1, crown would be N2. You look these up, flint has index of refraction of 1.66. That's flint glass. And crown glass, the outside layer, is 1.52, as we've said many times. That's crown glass. All right. And so we want to figure out what is, if I'm going to make a fiber optic cable and be able to snake it around, what is the critical angle for this? So theta sub c, again, going through the same math as we did previously, is again the arc sine or the inverse sine of N2 over N1. Theta sub c is the inverse sine. All right, N2 is 1.52, N1 is 1.66. We find that the critical angle for this fiber optic arrangement is, put in your calculator, 66.3 degrees. Again, a very high angle. All right, so that allows you to have all the twisting and everything. Right, so it's set up such that you have total internal reflection. Okay, so there you go. Real life situation. All right, so now change topics. That's the total internal reflection. Our next topic is called dispersion. Dispersion is the topic that describes rainbows and prisms. Okay, so everyone enjoys a beautiful rainbow, but why do we have rainbows? So what it is that white light is a mixture of the major components of visible light. So of the major components of visible light. We generally know those as red, orange, yellow, green, blue, and violet. From longest wavelength to shortest wavelength. Now, sunlight is composed of all of these components. So sunlight is more yellowish than anything else. There is, I would say, there's more yellow than anything else in sunlight, but sunlight does have all of the other components of the rainbow. Oftentimes, people will put sometimes they want to say Roy G. Biv. They put indigo in here between blue and violet. I mean, I generally just write it like this: red, orange, yellow, green, blue, and blue, violet. So longest wavelength to the shortest wavelength. You go shorter wavelength in violet, you go in the ultraviolet. You go longer wavelength in red, you go in the infrared. Okay, and this is a sliver, a thin sliver of electromagnetic spectrum. Now, these when our eye, so when our eye or eyes receive pure wavelength light, we tend to only see one of those 6 colors up there. Okay, but there's thousands of hues of colors. Again, we're looking at the major components: red, orange, yellow, green, blue, and violet. But our world consists of many colors. And so there's many more hues of colors out there. Okay, so basically the thousands of other hues of colors, the thousands of other hues that we can sense in other situations are our eyes responds to various mixtures of wavelengths. Okay. And so, as I said, sunlight is yellowish, but it consists of all 6 major colors in the rainbow, or all 6 major colors in the spectrum, the visible spectrum. Okay, and so now the sequence of colors of rainbows is the same as the sequence of colors plotted versus wavelength. And so if you give you a little plot here from the book. A moment here. So this is a plot from OpenStax, figure 25.22, and you see the colors of the rainbow: red, orange, yellow, green, blue, and violet. And you see that they range in wavelengths from about 760 nanometers all the way at the end of red, all the way to about, it's like about 350 nanometers or so for violet. Now, for wavelengths shorter than violet, you're what's called the ultraviolet, which means above violet. And if you're in wavelengths longer than red, you're the infrared, right? So again, this is one snippet of the electromagnetic spectrum. Now, it turns out that the sequence of colors that you see in a rainbow are exactly the same as the sequence of colors that you see in this plot. That the red is the longest wavelength and the violet is the shortest wavelength. So there's a reason for that. All right, and so going back to, so if you imagine taking light and putting white light into a prism. You notice that white light goes into a prism. On one side of this prism is nothing but a pyramidal shaped piece of glass. It's a glass prism. White light comes in and it gets what's called dispersed. And you notice that the rainbow that it creates is an exact same sequence that I just showed you. Red gets bent the least and violet gets bent the most. It all depends on the wavelength of the light, in a process that we refer to as dispersion. Dispersion, it turns out, if you're looking at this table here, 25.2, it turns out that the index of refraction of light is a little more complicated than what I first told you. It is not just a constant. It actually is a function of the wavelength. And so you notice that for any material, as the wavelength increases, as the wavelength, as the wavelength reduces, the index of refraction increases. So again, we're going, if you read this table, you go from red to violet, you're going from longer wavelength to shorter wavelength. So going from longer wavelength, reading from left to right on any column, you have each of these rows is a different substance. You have water as a top one, diamond, crown glass, flint glass, polystyrene, and fused quartz. These are all the various substances that we're passing light through. And the idea is that they have a response. They have a unique response, an index of refraction function of wavelength. Each one of them has their own function. But one thing they have in common is if you go reading across the columns, you're going from long wavelength to shorter wavelength. You're reducing. As you read the columns from left to right, you're reducing the wavelength. And as you do so, every single one of these substances increases in its index of refraction. Water increases from 1.331 to 1.342. Crown glass goes from 1.512 all the way to 1.530. Fused quartz 1.455 all the way to 1.468. Diamond goes from 2.410 to 2.458. Every single one of them, as wavelength reduces, index of refraction increases. Okay, and so that particular behavior means that if you apply Snell's law, the law of refraction, each of these colors is bent differently, because each of these colors of light, each of these components has a different index of refraction. And that is what causes the rainbow. All the colors are bent differently. All right, and so let me write this more in words here. Can you see the data? And in fact, we're going to use this kind of data to solve problems. So dispersion is simply this. The index of refraction. All right, so the index of refraction N of a given material is a function of wavelength, or is a function of the wavelength of light. Lambda. So we can write the index of refraction as n of lambda. Write it even in functional form if we wish. N as a function of lambda. One thing to point out is that for all materials, I don't know, I would say all, but these are the materials that we're looking at. I'll say all, but I might be incorrect about this. But for all materials, or we'll say most. I want to make a generalization if I actually don't know. So for most materials, these are the ones considered in this book. As wavelength reduces, the index of refraction increases. All right, so what does that mean? Well, since red has a longer wavelength than violet, violet will have a higher index of refraction and it will be bent more. And in fact, it'll have the highest index of refraction of all the visible light. It'll be bent the most. I'm just comparing two things, comparing one end of the spectrum to the other. So red is bent the least, violet's bent the most. And you have the dispersion of colors because of a prism. You see this not just with a glass prism like I just showed you. You see these are raindrops. Anytime you're passing light through a medium, you're going to have refraction. I showed you a number of materials in that table. Water, glass, flint glass, crown glass, diamond, polystyrene, you name it. All of them will have an index of refraction that is a function of wavelength. They'll all bend the colors of light differently. So you will always have dispersion of light. That is because the index of refraction is a function of the wavelength of light passing through it. All right, so let's do some problems here with rainbows. All right, so I'm going to do OpenStax 25.28. And that says, A, what is the ratio of the speed of red light to violet light in diamonds? Based on table 25.2, which is the table I just showed. Okay. B, what is the ratio in polystyrene? Which is more dispersion? C. All right. So OpenStax 25.28. A, what is the ratio of the speed of red light to violet light in diamond based on table 25.2? B, what is the ratio in polystyrene? So Cutnell Johnson will have its own table like this. And then C, which is more dispersive? All right, so diamond first and polystyrene second. All right, so how do we do this? And you need a table of data. I don't know, I don't recall which there. I mean, there definitely is in chapters 25 or 26. There's definitely a table when you talk wherever the section is on rainbows and prisms. Okay, so part A. Well, let's see. Let's do red. So again, we're talking about diamonds. Okay, diamond is the substance which we're passing light. A, so speed of red. V red will be the speed of light divided by N red. Okay, so that's how you define it. The speed of light is always less in a material. So again, it's always the speed of light in a vacuum divided by the index of refraction of that material. So we want to figure out what the speed of light in red is. Okay, in diamonds. Okay, so again, we have to go and say, okay, well, let's see, 299,792,458 meters per second. That's always the speed of light in a vacuum. But that's not the speed of light in diamond. The speed of red light in diamond. You look up diamond. Say, oh, what's N red in diamond? Oh, it's 2.410. Okay, 2.410. That's the index of refraction for red light in diamond. So the speed of light in diamond, red light that is going to be 1.244 times 10 to the 8th meters per second. All right. What about violet? So V violet will be the speed of light, again, in a vacuum divided by N violet. Well, again, speed of light in a vacuum is always 299,792,458 meters per second. And we look up the index of refraction of violet. Now, again, for diamond, looking up that row in the table for diamond. Okay, nothing else, diamond. All right. And you find out that's 2.458. So again, the index of refraction has increased relatively significantly for going from red to violet. And you do there, you have that the V violet will be 1.220 times 10 to the 8th meters per second. All right, and you want to form a ratio, V red over V violet. So let's make a ratio of these two speeds. V red over V violet will be the 1.244 times 10 to the 8th meters per second divide, which room do I have here? 1.220 10 to the 8th meters per second. All right, that ratio we find out is 1.02. All right. So done. These are the answers for part A. We want the I guess we just want the ratio for part A. Okay, so we want the ratio. So the answer we want for part A is this guy. All right, so part A for diamond, we come out and say, okay, well, diamond is kind of put this in a parking lot. V red over V violet is 1.02. Again, it's a pure number because you're taking a speed divided by a speed. All the units will cancel out. What about polystyrene? Okay, so B, we look at another row of the table. And let's see here. B is polystyrene. All right. Do the same calculation. All right. V red is the speed of light divided by N red. All right, so make sure you read the correct row in the table. So 299,792,458 meters per second. Again, it's the speed of light in a vacuum. We look up N red for polystyrene. And we find out that N red for polystyrene is 1.488. So V red will then be 2.015 for 78 meters per second. That's V red. How about V violet? V violet. Again, same old here. Speed light in the vacuum divided by N violet, again for polystyrene. You're looking at that row for polystyrene. 299 792.458 meters per second divided by 1.506. Find out that V violet, V violet is, for polystyrene, is 1.991 of 78 meters per second. And we form the same ratio, V red over V violet, just like we did for diamond. Form that same ratio. We get 2.015 times 10 to the 8th meters per second divided by 1.991 times 10 to the 8th meters per second. Get meter second over meter second cancel out. We find out that that ratio is going to be 1.012. Not really much of a difference in speed. We still do see the, so the question is, okay, well, we have that particular one. We have for part B, we have that our answer is V red over V violet is 1.012. So part C is, which one is more dispersive? All right, so which one is more dispersive? So all you have to do is take a look at these two ratios. And the ratio V red over V violet for diamond was larger than that for polystyrene. So diamond is more dispersive. All right. That is problem 25.28. Let's look at OpenStax 25.29. A beam of white light goes from air into water. At an instant angle of 75.0 degrees. Okay. At what angles are the red? So at what angles are the red? And they give you 660 nanometers in this case. A little bit less than what I normally see red as, but okay. And the violet, (410 nanometers), they specify. Parts of the light refracted. Okay. So a beam of white light goes from air into water at an instant angle of 75.0 degrees. At what angles are the red, 660 nanometers, and the violet, 410 nanometer parts of the light refracted? So this is your rainbow. This is what you see when you have light in the sky passing through droplets of water. You see the beautiful rainbows after a storm. Okay? Or you see it as you spray water on a summer day. Okay, so let's erase this for real estate here. Okay. So what is the governing equation? Well, it's Snell's law. So use Snell's law, or otherwise known as the law of refraction. And that is N1 sine theta 1 is N2 sine theta 2. Now, in all cases, so essentially what we're looking at here is we're essentially looking at following problem, right? We have light that's coming in at a large incident angle. It's supposed to be 75 degrees. My picture doesn't really show that. This is theta 1. And it's in N1, which is really air. All right, so it's going to be N air, really, but I'm going to call it N1. And it refracts, it bends toward the normal. And it's going to be going and refracting at an angle to an angle theta 2 from the normal. And this side of the interface has index refraction N2, and this is water. Now, they are giving you, in all cases, they're giving it theta 1. Theta 1, they're saying you have 75-degree angle, incident angle of the light. It's a white light. All of the components of light going through air are at the same angle. They're all coming in together as a single beam. Red, orange, yellow, green, blue, violet. All of them together, mixed together, make white light, coming together in a beam. Incident, an array, incident at theta 1 with the normal of this particular water droplet or whatever it is that's going into. It's a mass of water. Okay. N1, we can look this up. Well, we know the index refraction of air again is 1.000293, and index refraction of water, we can look that up too, as 1.333. All right, so these are all this data that we can all look up, and what we're looking for is theta 2. And we want it for red and violet. And we're going to compare the two, right? So each beam of light, each component of light is coming in at the same incident angle, but it's refracting differently, it's bending differently. Let's see what those angles are. So what do? We go to Snell's law. Oops, I miswrote Snell's law. All right, sine theta 2. I don't know what I was thinking there. There you go. All right, so I need to solve for theta 2. So let's go through the math one more time. I'm going to flip about the equal signs. I have N2 sine theta 2 is N1 sine theta 1. Snell's law. What do I want? I want theta 2. So I'm going to get it by itself, right? So I'm going to divide everything through by N2. I get the sine of theta 2 is N1 over N2. That fraction is multiplied by the sine of theta 1. And what do I want to do now? Well, I want to get the theta 2. It's the argument of a sine function. So I take the arc sine or the inverse sine of each side. So I get the theta 2 is the arc sine or the inverse sine of all this stuff on the right. And that is the ratio N1 over N2 multiplied by the sine of theta 1. Right? That's what I want to use. That's the equation I want to use. I want to do it for both I'm gonna do for both red and violet. Okay, so this is what I get this out of. Again, all of geometrical optics is based on two equations: the law of refraction, or Snell's law, and the law of reflection, also called Hero's law. All right, so in this particular case, when I'm talking about bending light, transmission, and the next topic is going to be lenses, we're going to be using an application of Snell's law. When we get to mirrors, we'll be talking entirely about Hero's law, or the law of reflection. All right, so this is what I have here from Snell's law. So let me write this now. I'm going to do it for red, and I'm going to do it for violet. So give myself some space here. So theta to red. Remember what we just wrote down. Inverse sine of what? Well, I said n1 over n2. Well, that's going to be, n1 is always going to be, actually, I am mistaken here about n2. Erase that. This is the index of refraction of water, but we don't know what that is yet. So I gave you an average value. We need to look that up, right? There's going to be one value for red, one value for violet. So please cross out what I just said a moment ago. Wasn't thinking. Okay, here we go. Index refraction. So again, as I said, n1 over n2. n1 is always going to be the error, 1.0000293. The n2 in this particular case is going to be, well, you know what? Let me write one more equation. So again, it's going to be n1. It's going to be n2 red. The index of refraction for red in what? Water. I got to look. I have to, that table I showed you. I need to look at the row for water. Okay, and then again, it's going to be sine of the incident angle theta 1. All right, so let's do this. So theta 2 red is the arc sine, or the inverse sine. What's n1? Well, it's error, 1.0000293. n2 red, the red light in water. If I look that up, red light in water is 1.331. Not 1.333. I gave you the average value. I apologize. 1.331. And then sine of the incident angle, which is 75 degrees. When I do that, I will find out that theta 2 red will be 46.5 degrees. That's one of my answers, all right? So one of my answers is theta 2 red equals 46.5 degrees. Okay, great. Now I want to do theta 2 violet. Well, it's the exact same math. Instead, I can substitute everywhere I see red, I can put violet. So theta 2 violet. Inverse sine of n1 over n2, not red, but violet. And again, that's all multiplied by the same sine of theta 1. And so what I do is I now put the theta 2 violet into the numbers. The numerics for theta 2 violet is not 1.331, but it is 1.342. Everything else being the same. And I come to find out that there is an angle of 46.1 degrees for violet. Yeah, it's the same problem, but it's a little different angle. Again, that's the dispersion. Violet has an angle of 46.1 degrees. Red, 46.5 degrees. All right, and so you might say to yourself, well, hey, Why would violet have a smaller angle than red? Well, you look at it, what you're seeing here is that red is going to be closer to the, violet is going to be closer to the normal than red is. If you look at the rainbow, it goes from the farthest out red all the way to the furthest in violet. So violet, all this 6.1 degrees means is that violet is 0.4 degrees closer to the normal than is red. Violet gets what? Violet gets bent more, has a smaller angle of refraction. Violet gets bent more than does red. That is why violet has a smaller angle than does red. And any other intermediary angles would be bent somewhere between 46.1 and 46.5. That's your dispersion. That's what causes your rainbow. All right, so these are my answers. Theta 2 violet, theta 2 red. Okay, we'll do one more rainbow prism problem. OpenStax 25.32. All right, so OpenStax 25.32. A parallel beam of light containing orange, orange is about 610 nanometers, and violet. And the wavelength we take for violet in this problem is 410 nanometers. Okay, wavelengths goes from fused quartz to water. Okay, striking the surface between them at 60.0 degrees incident angle. What else? What is the angle between the colors and water? All right. All right, here we go. OpenStax 25.32. A parallel beam of light containing orange, 610 nanometers, and violet, 410 nanometers, wavelengths, goes from fused quartz to water, striking the surface between them at 60-degree incident angle. What is the angle between the colors and water? So again, this is another application of Snell's law, as is many things, or most things in this study. All right, so let's remember this. All righty, so what do we know? Again, we're going to employ Snell's law. So again, use Snell's law, which is true in pretty much everything we're doing here. Or Snell's law, otherwise known as the law of refraction. N1 sine theta 1 equals N2 sine theta 2. All right, there you go. What do we know? Well, we know N1 orange. Okay, so we're going to have indices of refraction that, that the colors are going to have certain index of refraction in one material, the quartz, and in another material, the water, right? And so again, N1 deals with what? We're going from quartz, or fused quartz, I guess, to water. So we need to look up N1 and N2 for each of these substances, right? So looking it up, we have, okay, let's see here, N1 orange. A laundry list of stuff we need to look up. So for orange light, in fused quartz, it's 1.456. Violet light infused quartz, N1 violet. You look that up, it's 1.468. The incident angle, well, let's see, let's look up N2 orange. N2 orange. This is for water, orange light and water. What's its index of refraction? 1.332. And the index of refraction in water for violet light, N2 violet, that's going to be 1.342. See that number in the last problem. Okay, incident angle, we also know that. That's 60 degrees. We know that as well. So all these various things that we come into the problem knowing or being able to look up really quickly in our table. All right, so now, remember when we solve for the for theta 2, again, I'm not going to go through the same math. You're curious, look at the previous problem, but we're going to look at it and say, okay, well, let's do, first of all, let's do the orange light. All right, so theta 2 orange will be the inverse sine. We're following the orange light. N1 orange divided by N2 orange multiplied by the sine of 60 degrees. Okay, again, what did we do? Well, we flipped about the equal sign. We had N2 sine theta 2 is N1 sine theta 1. We divided both sides by N2. We took the inverse sine. But we have to be careful. Well, in the past, I would say N1 over N2 sine of incident angle. But I gotta be explicit though. I'm watching the orange light. The orange light has a particular wavelength. I'm sorry, a particular index of refraction in fused quartz, and it has a particular index of refraction in the water. And so what I need to do is I need to specify one more subscript, and that's the color. In this case, everything is orange. I'll do the same calculation again for violet. All right. So again, I have to be very specific about what color light am I talking about. I'm focusing on orange and I'm focusing on violet. I'm not, in a previous problem, I just said, oh, you have a beam of white light. And I just considered everything being at the incident angle. Well, now I'm particularly looking at orange and I'm going to look at violet. All right. So again, if I do this, what do? Well, I'm going to just plug in values. So theta 2 orange is the inverse sine N1 orange, 1.456. N2 orange, 1.332. again, times the sine of 60 degrees. I find out that theta 2 orange. When I work this math out, again, I take the fraction, multiply by the sine, and all of this is inverse sine. That's argument has, you take the inverse sine of that. You do that in your calculator, you find out that theta 2 orange is 71.199 degrees. So theta 2 orange. We'll write this down as 71.199 degrees. Okay, what about violet? Again, it's the exact same math. Everywhere I see orange, I erase that and put violet. And you can't do that. This is separate algebra for you. For me, I got the whiteboard. So I have theta 2 violet is N1 violet over N2 violet times the sine of 60 degrees. Well, I have different numbers now. I have 1.468. Again, this is violet. .468, and then the N2 violet is 1.342. 3 becomes 4. All right, and when I do that calculation, I find out that the answer is 71.323 degrees. All right, so theta 2 violet is equal to 71.323 degrees. All right, so I have the angle which orange light makes in the water and the angle that violet light makes in the water. And what do I want? I want the angle between them. Well, it's just the difference angle. All right. So that last part of the calculation is very easy. I want delta theta. So delta theta is just theta 2 violet minus theta 2 orange. Delta theta will then be 71.323 degrees minus 71.199 degrees. Remember, these angles are pretty close. The difference of the angles, the angle between the angles, if you will, or the angle between the rays of light, the orange light and the violet light in the water will then be 0.124 degrees. And it's rainbow, it's dispersion. All right, so that's dispersion. Now, when you have a new concept, if you will, the concept of refraction, I mean, that we're talking about, can you have a concept, what do you want to do with it? Well, again, it's the whole concept of STEM, right? You know, once you know science, or really mathematics comes first, then you have the science. Then after that, you start talking about and trying to make something. That's the engineering. And there's the T in STEM is the technology. That's when you have a bunch of engineering items, and that's your way of life, is that you live in this technology. That's your T. So again, the STEM is set up to make a cute word, but the actual STE and M in there actually are in a different order. All right, so we now have a understanding of refraction of light. Well, let's go make something. So one of the typical things you want to make are lenses. So we have lenses for all kinds of devices, including eyeglasses and microscopes and telescopes. So we have this concept of a lens. And that's what we're going to talk about here. And so lenses are found in a wide variety of applications, a wide variety of applications. Including eyeglasses, telescopes, microscopes, cameras, you name it. You can go on and fill more things in if you wanted to. So again, we live in a world where lenses are very important, okay? Now, the important thing about a lens is we want to use a lens to form an image, right? So a lens uses refraction of light. To form images. Now that image might be something you project an image on a screen, or it might be you project an image on a film. But the important thing is you're forming an image. Okay. Lens, the word lens derives from Latin. Derives from Latin. For basically a lentil beam. Since the shape of a convex lens looks like a lentil beam. We'll see that in a moment. Shape of a convex lens is like a lentil beam. All right. So again, lenses are found in a variety of applications, including eyeglasses, telescopes, microscopes, and cameras. Lens uses refraction of light to form images. The word lens derives from Latin for lentil beam, since the shape of a convex lens is like a lentil beam. All right, that's where the word lens comes from. Now, the idea is a lens is shaped to form an image, right? So it's so a lens is shaped to control the refraction of light beams, or light rays, to form an image. All right, so probably one of the easiest ways to look at this, so I'm going to show you kind of a picture here. I'm going to show you a picture of OpenStax, so give me a moment here. We'll see how lenses work. Let's do a real close-up first. All right, I'm going to look at OpenStax 25.27. Share my screen. The first kind of lens we want to look at is called a converging lens. Now, if we look at the picture on the left, I mean, really the picture on the right is the actual full lens. So we're looking at parallel rays of light coming from the left. Let's look at the rightmost picture first. Parallel rays of light enter the lens on the left. The lens is basically either some shaped piece of glass or piece of plastic whose purpose is to use refraction to its advantage in order to be able to focus light on the other side of the lens. All right. And so you see that the rays of light bend, and they bend in such a way that the lens causes them to focus at a location on the other side of the lens called capital F, which we refer to as a focal point, or focal point. Yeah, the focal point. The distance, little f, you see in this picture, is the distance from the center of the lens to this focal point. Focal point is where parallel rays of light converge. This is called the focal length. So that capital F is the focal point. I'll write this down in a moment. That is the location where the lens is, again, this is what we call a converging lens. We'll find out there's two types of lenses: converging lens and diverging lens. A converging lens has a purpose of converging light to a focal point on the other side of the lens. Again, so what we're looking at is a special case of parallel light coming from infinity, striking this lens, and all of it bending in a different way because of the way the front and back surfaces of the lens are shaped. And again, this is the application of Snell's law, both of the front surface and the rear surface, that allows the light to be bent in such a way as to focus at a point, capital F, called the focal point on the other side of the lens. The distance between the center of the lens, or the central plane of the lens, and this focal point is called the focal length. Now, the left-hand picture shows a blow-up of just what happens to one ray. Looking at ray number one, these rays, you look at the right picture, you have ray one, it goes into the top of the lens. Ray 3 goes through the lower part of the lens, and ray 2 goes through the center of it. Looking at ray 1, we see that close up, its shape is different than the front surface and the back surface. But anyway, look at it though, it's always going to refract with respect to the normal. So it's going to come in at a certain incident angle, depending upon the local normal of this curved lens. It's going to refract according to Snell's law. It'll go through the lens in a straight path, and then again it'll have another refraction. So let's say the first one is air to glass. The second will be glass back to air. And what's it going to do there? It's going to refract away from the normal. And the combination of those two actions, those two interfaces, or just two applications of Snell's law, cause it to refract toward the focal point. I mean, that's what's going on. You have two refractions, one at the front surface and one at the rear surface. The front surface, the refraction will be going from air to glass. The light beam will refract toward the normal at that particular local normal. Again, every normal is going to be different because this lens is shaped in a convex polygon. So every lens is going to be different. Every normal is going to be different. It's not all going to be the same normal. It's going to be a normal to a curved surface. So again, that local normal, the light will refract toward the normal. It'll go through the glass or plastic, whatever it is, in a straight path, and it'll have one more refraction, one more interface. And this time, we're going from glass to air. So we're going from a higher index to a lower index. And so what's going to happen is that the normal will be different, of course, and the light ray will refract away from the normal. In these two refractions, front surface and back surface, is what causes the rays all to focus at focal length at the focal point capital F, which is a focal length little f away from the center of the lens. All right. So what we see here in this picture, this is OpenStax 25.27. Let me stop sharing for a moment. What you see in OpenStax 25.27 is an example of a converging lens. Let me kind of write down what I just said in words. So, get another pen here. So OpenStack's 25.27, or I'm sorry, OpenStack's figure 25.27 showed a converging lens. Well, actually, we'll say it showed a convex lens. Okay, so let's talk about what convex means. Convex has nothing to do with physics. Convex is a shape. Okay, so what did you just see? Well, you saw a lens that was formed like this. It had a part of a circle, and over here was a part of a circle. Okay, each of these circles, this particular circle here, this outer, and of course, what you have is a lens axis. Okay, that goes through the center. This is the axis. That goes to the center of the lens. Okay, and so what's happening is you're looking at a ray of light that's parallel coming up along here. This was called ray 1, if you will. Well, in the front surface, it's going to meet a normal, and looking at the local curvature, that normal is going to be pretty much like this. And so it's going to bend what? It's going to bend toward the normal. Doesn't look very good. Let me draw this bigger. All right. Make this a little exaggerated. Okay, here's my central axis. All right. And I'm looking at a ray of light that's coming toward the top. We call this ray 1. This is parallel, a light that's parallel to the axis. The picture doesn't show that. Now, locally, I have a normal. Oops, I have a normal everywhere on this curved surface is a normal. I explained to you, in some cases you have a normal that's everywhere the same, like a flat surface. And I showed you, remember, a picture of a globe, or I brought out a globe and I showed you that everywhere along the globe was a normal is radially outward. So a curved surface has a normal that's different depending on where you are. So here you have an angle of incidence, say theta 1. All right, what's it going to do? Well, it's going from air to say glass back to air. So it's going to bend toward the normal in the glass. We'll try to draw this. It's going to go all the way across, straight line, same material. And so there's no reason for it to refract inside of the glass. And it's now going to do what? It's now going to come into contact with yet another normal. This normal is different, however, because this normal is the curvature is the opposite of what the previous curvature was, and I'll explain curvature here more in a moment. You have a different normal. What happens now is that, well, now the angle of incidence is this theta 2. Again, it's the same angle of incidence that happened up here as well, but now the light's going to bend away from the normal. And again, it's not a very good picture, but it'll be at a bigger, call this theta 3. Theta 3 will be bigger than theta 2. So theta 3 will be bigger than theta 2 because n air is less than n glass. All right, and so again, the light always bends away from the normal when you're going from a higher index to lower index material. Now, that's what you saw in the picture. And all these rays of light are going to do the same thing. This is bent in such a beautiful way that depending upon where the ray of light is, it will be refracted at the front surface and the rear surface such that they will all focus at that focal point on their side. F, it again, is called the focal point. Focal point of the lens. Okay, little f is the focal length. Of the lens. What is the focal length? It's the distance between the center of the lens. You draw a plane right through the center of the lens. It's the distance from the center of the lens to this focal point, little f, okay? So that is the distance from the center of the lens to f, the focal length, the focal point, all right? That's called the focal length. So we have a focal point and the focal length. Again, two new terms in optics. Very important. Now, this is called a converging lens. So this is a converging lens. So this is a converging lens. Because it causes light to converge to a focus, to a focal point. All right. So that's why it's called a converging lens. There's two types of lens, converging lens and diverging lens. So what does this word convex mean? All right. Well, convex, let me erase a few things here. So what you have with convex, well, let me erase some words here. So let's talk about, okay, that's a converging lens. And the reason why it's converging is because its purpose is to cause light to converge to a focal point, okay? So it turns out that converging lenses are convex lenses. Convex is a geometrical term. And what you can look at here is that, and this is the axis again. This circle, so you have an object, you have light coming from an incident direction, okay? This is the side where we'll put an object. Incoming light will meet a curved surface whose radius is in the direction opposite to where the light is coming from. So you look at this particular this first surface. Well, it's part of a circle. You're to continue along. You can actually draw a circle. This is all part of a big circle, right? This circle would have a radius to it. And this radius is called the radius of curvature. You imagine this part of the lens is all part of a circle that you don't see. It's part of a circle. And that circle has a radius. That radius of this circle is called the radius of curvature. So the radius of curvature for a convex for a convex lens, the radius of curvature for the surfaces of a convex lens are directed inward or radially inward with respect to that surface. Purely a geometrical term. You have what we call an inward normal and outward normal. And so again, this particular circle is radially inward. So again, compared to the outside surface, you're looking at the edge of a circle. You're trying to get into a circle. Okay, the circle is not where you are. The circle is external to where you are. So the ray's coming in, and it is trying to actually get into a circle. Now, if I look on the other side, I mean, it works both ways. This is also part of a circle, this second surface. And again, anything that's happening here at the focal length is also outside of that circle. So you're talking about a radius of curvature of a circle that is radially inward from the surface. That is what you call a convex shape. Okay, convex shape. When we talk about convex simply means has to deal with a geometrical shape. Is where is the radius of curvature? Where is the circle compared with the outside surface? You know, we'll in a moment talk about concave shapes where you're actually coming from inside the circle. Concave shape is the exact opposite of convex. Convex, the circle is always external to you. So again, the incident light approaches this particular surface. Well, this surface is part of a circle that is elsewhere, if you will, from this first region. Okay, so again, the circles, you're looking at the outside surface of the circle. Whereas on the other side, the inner shape of the lens, again, you're looking at the outside of a circle. Again, the circle would be then drawn like this. On the other side. And you're always, wherever you happen to be with respect to the lens, you're always outside of that circle for which that surface is part of. That's what convex means. Convex is a statement of shape, is a statement of geometry. Converging, on the other hand, is a statement of what happens to light rays. So it turns out that converging lenses are convex lenses. Okay, so looking at this, we see that for lenses, convex lenses are converging lenses. Crazy. All right, let's see. Am I still on? Yeah. It's moving too much. All right. All right, so I'll make that improves. Convex lenses are converging lenses. All right, convex lenses are converging lenses. Let's see if that improves things. Okay. Now we have another type of lens that we use, and it's called a concave lens. Let me give you a picture of that. So again, convex means shape. Converging means what does it do to light? Let me go back to the OpenStax book and look at a different shape. You're looking at parallel light. Share my screen. All right. So I showed you before was a convex lens. What you now see is what we refer to as a concave lens. Let's look at the bottom of the two pictures first. Again, we're going to focus on ray number one. Well, ray number one now is again, it's going to see a front surface. There's going to be a local normal to that surface, and light will, the way it happens is, like, again, light will bend toward the normal. It'll go to the back side where you have the glass air interface, and it'll bend away from the normal. What you see is that the concave surface, again, I'll explain why it's called concave in a moment, diverges light. Parallel light diverges. So rays actually will diverge away, but they seem, if you were to extract or extrapolate the rays backwards, they all appear to come from the focal length, a focal point on the same side of the lens for which light is coming from. So this is a diverging lens, and the interesting part of it is that the focal length is on the same side, or the focal point is on the same side of which the light is coming from. So this, and if you take a look at the top picture, again, it's a blow up. You see that you have an incident angle θ1, the light comes in. Again, it's all about the shape. It's all about the normal is all with respect to the local location of where the light is striking the curved surface. And again, depending upon where the light strikes the curved surface, the normal will be different. Once the light transmits into the glass or the plastic, whatever the lens is made out of, it'll go straight through, and then it'll meet the other surface, which we will call it the glass air interface for this case. In that case, you're going to bend away, and given that the nature of these normals, that's going to cause a divergence of light. Light will diverge. Okay, and it'll actually form a focus on the same side. All right, let me stop sharing for a moment. Okay, so drawing that picture, what we now see, the lens looks like this. Skinnier in the middle, fatter on the outside. Here's our lens axis through the center. All right. Now we're considering, let's say, a ray 1 coming in, again, just like in that picture. And let me lower that ray a little bit so I can actually draw it. So let's consider a ray 1 maybe over here. All right, so it's going to have a local normal. It's going to, again, bend toward the normal, go all the way across. Another local normal, bend away from the normal. And there's where it ends up. It diverges. Two such rays, say ray 3, do the same thing. It diverges. If you extrapolate the rays back, again, the diverging rays, extrapolate that ray back and extrapolate this ray back, they will converge on a focal point on the same side for which the light came. Its focal length will also be the distance from the center of the lens, imagining this being the center of the lens. Oops. The center of the lens to the location of the focal point. Now, this is called a concave lens. Why? Because if I look at the front surface and I continue drawing my circle, the radius of curvature is on the same side from which light's coming from. If you look at the other side of the surface, again, it also forms a circle. And so when you're on the outside of one of these surfaces, you're within the circle where the radius of curvature is. Before, you're always on the outside of the circle. You're never in the circle. Now you're in the circle. So again, a concave shape is one where the outside of the surface, of each surface, is within the circle defined by the radius of curvature. Okay? Whereas that's a concave. Concave deals with shape. Previously, I said convex. So convex shape is one where the where the outside of each surface is outside of this circle defined by the radius of curvature. Okay, so again, convex and concave deal with the shape of the geometry, the shape of the lens. Now it turns out that this concave lens is what we refer to as a diverging lens. Why? Because it takes parallel light and it diverges it. Its purpose is to diverge light. So a concave lens is a diverging lens. A convex lens is a converging lens. Again, converging and diverging mean what happens to the rays of light. The rays of light come to a focus on the other side of the lens. The ray for a converging lens, the rays of light diverge away, and the focus appears to be on the same side of the lens as the light. Convex lens is a shape. You know, convex, concave, those are shapes. That's pure geometry. Now, what's interesting, if I make a side-by-side comparison now of the two types of lenses, let's look at a side-by-side comparison. The convex lens and a concave lens, let's kind of look at what they do. Again, we're just looking at parallel light right now. What happens to parallel light? So again, I want to look at the convex converging lens. And I'm going to compare that with the concave diverging lens. Let's compare the two. All right, so again, I have the convex lens. Here's the axis of the lens. Okay, now again, what happens to parallel light? Here's parallel light coming in, and it focuses on the other side at a focal point F, which is a distance little f away. Again, focal length. Again, this is parallel light. Parallel light. Converging lens converges. Now, what happens to diverging lens? Well, diverging lens looks different. It's fatter on the outside, skinnier on the inside. And here's the axis. Parallel rays of light will diverge away. Oops, draw this again. Again, lens fatter on the outside, skinnier on the inside. Here is my axis through the center of the lens. I have parallel lights. One ray on top. Try to be more careful here. Do this again. Let's not make it so high. Okay, what's going to happen is it's going to diverge away. And it's going to look as if it is, if I extrapolate those divergent rays, it's going to look like it has a focal length F on this side. I'm sorry, focal point F, and it's going to have a focal length here. Now, what's interesting here is that the purpose of, again, this is parallel light coming in. And actually, there's a think of parallel light going down the axis too. The converging lens actually focuses light. If you were to make a magnifying glass out of this, you can burn something. You can take some sort of leaves or something on a very hot day, get a magnifying glass with a nice converging lens, and you can actually burn something. You can actually focus light to actually burn something. Actual light gets here. So this is what we refer to this as real. We would actually have a real image. Why? Because light actually converges at the focus, at the focal point. Okay. On the other hand, if you take a concave lens, light diverges away. And yes, I see an image right here, but if I were to actually try to put a piece of paper where I see that image, I'll see nothing but diffuse light. If on the other hand, if I go on the other side of the lens and try to put a piece of paper to see anything, all I see is diffuse light. What we actually see is a virtual image. Light does not actually converge here. It appears to converge there. So this would be considered a virtual image. A virtual image. Light does not converge at a virtual image. It appears to converge. Okay? So yeah, you definitely see an image there, and then we record on our retinas because we actually will record this as a real image on our eyes. But that actually, there's no image that's actually being formed there. Light does not converge there. It only appears to converge there. It's called a virtual image. Okay, so the idea is the real side of a lens is what is a lens supposed to do? A lens is supposed to transmit light or allow light to transmit through the lens and go to the other side. That's what's supposed to happen. When light does that, that's a real image. When you see light having an image on the same side as where the light came from, well, that is what we call a virtual image. Light does not, and that's not the purpose of a lens to have a virtual image. Light is not, the image is not supposed to be on the same side of the lens as the object or as the light. We refer to that as a virtual image, all right? And so we would actually call the focal length of a real, for a real image or a focal length of a convergent image, we actually call that positive. So this is a positive focal length. Define it as a positive focal length. F for a converging lens or a convex lens is positive. It's where, again, the other side, this is considered the positive side of a lens. Where the light actually came from is considered the negative side of the lens. What's the lens supposed to do? It's supposed to transmit light through the lens. So again, light goes on the other side, becomes positive. Light, anything that's on the same side is negative. So a focal length of a converging lens is actually a positive focal length. We actually refer to a focal length on the same side of the lens as a negative focal length. So a concave lens has a negative focal length. So you have to be very careful. Lens, optics calculations are probably about as easy to calculations you'll find in physics. The only place you can get tripped up is these signs. These signs mean everything. If you get the signs wrong, your answer is going to be utterly wrong. So it literally is the calculation you'll find in mathematics and optics is about as simple as can be, but where you can trip up is on signs. So again, a convex lens, which is also a converging lens, has a positive focal length. A positive focal length is the length between the center of the lens and where the focal point is. How do you find the focal point? You allow parallel rays from infinity to come in, strike the lens, and see where you have a focus. So I would, in the lab, you would just go and imagine a light source far away and take a piece of paper or some sort of a screen and figure out where do you see the light focusing. Ah, there it is. That's the focal length. The distance is, that's a focal point. The distance is a focal length. On the other hand, you'd have to kind of, it's a little bit harder to find a focal length of a virtual image because you can't do that same paper test because the actual light does not converge there. It only appears to converge there. You can't just put a piece of paper behind on a concave lens and say, okay, well, where does that converge? Well, that's harder to do because there actually is no light actually converging there. All right. So convex and concave are deal with geometric shapes. They're the shapes of the lens. Convex lens, concave lens. What does a convex lens do to light? It converges it. It's a converging lens. What does a concave lens do to light? It's a diverging lens. A convex lens gives you a real image. Sorry, I said that backwards. Let me start over again. So a convex lens converges light, gives you a real image. A concave lens diverges light and gives you a virtual image. All right, very important terms here. All right, so now we also talk about the power of a lens. Okay, this is an unfortunate double use of a term in physics. And we have enough of a problem with, the vernacular of using physics terms. But now we have a double use of a term in physics, and it's called the power. And the power has nothing whatsoever to do with the power that you've learned in physics so far. Completely different. Okay? The power of a lens, P, is defined as 1 divided by the focal length, where the focal length, now again, I've always told you so far in this class that, you're just dealing with lengths, and so you can actually be a little bit more loose with your units. If you want to keep them in centimeters, that's fine. Well, the focal length is a little, when you talk about power, it's the only time where you have to worry about your units, right? The focal length must be in meters. So the power is in what are called diopters. So when you see diopters, that's usually a capital D. So the power of a lens is a statement about how fast does it converge, how fast does it converge light. Again, it's in diopters, has nothing whatsoever to do not confuse, do not get this confused. Do not get this confused with mechanical power or with power equaling the change in, we'll say the change in work with respect to time. in watts. Absolutely different concepts. All right. It's unfortunate that we have a double use of a term in physics, but lens power has nothing to do with energy, has nothing to do with the time rate of change of energy. It nothing whatsoever. Do not get this confused. Lens power deals with nothing more than 1 divided by the focal length. Okay, you talk about lens power, it's 1 divided by the focal length. It is totally different. It's unfortunate, again, that we have this double use of terms. Okay, so all right, so the next thing we'd like to do is actually look at forming images with lenses. And so this gets us into a concept called ray tracing. All right, and so ray tracing is, as the name implies, you are literally following rays through a lens from the object to the image. All right, so we're going to now look at ray tracing. Now, when you do ray tracing experiments, sometimes you're doing ray tracing. It's almost like you're doing art. Like when we actually do optics labs, when we do ray tracing, it's almost like the physics class has suddenly changed into an art class. Everybody's out drawing lines and getting everything, the tracing rays. And so that's really, what it comes down to. So ray tracing, it's literally a technique. It's ray tracing is a technique of determining or following or tracing the paths that light rays take. So we're going to follow light rays, more or less. All right. So again, for rays passing through matter, like lenses, rays passing through matter, the law of refraction is used to trace the paths. Okay, and so ray tracing will find that we generally have to trace 2 or 3 rays. To map each point on an object to its location on an image. All right, so literally we'll have to go and take every single point, like say a person, like let's say, some object, like, let's say you're trying to look at a chess piece, you want to push it through a lens and see what it, what it looks like on the other side of the lens. Well, you have to take the top of the chess piece and maybe some other part of it, and every single point will map to its image, right? Well, we want to make an approximation to do that. We're going to make what's called a thin lens approximation, first and foremost. So we'll employ what's called the thin lens approximation. Okay, what that says is a thin lens is defined to be one whose thickness allows rays to refract but does not allow properties such as dispersion or aberration. And in general, you really want to talk about, even though there's two refracting surfaces, we'll consider one refraction. So even though the lens has two refracting surfaces, the front surface and the back and the rear surface, we will consider the ray of light only refracting once. In this approximation. Okay, that's the approximation. So again, we employ what's called a thin lens approximation to our study of lenses and ray tracing. A thin lens is defined to be one whose thickness allows rays to refract, but does not allow properties such as dispersion or aberration. So nothing more, no complicated lens property. Dispersion again is what we talked about with our discussion of rainbow. And aberration would be additional refractions or reflections caused by some irregularities in the lens. We're gonna make the assumption the lens does not have those problems. We have nice simple geometry and a thin lens. So even though there's two refracting surfaces, a front and a rear surface, we'll only consider the ray of light as refracting once. Okay, it's going to have one refraction. So then we're going to employ some rules for ray tracing. Right, and so we're going to kind of look at these various rules for ray tracing, and then we're going to use these rules to form images in different scenarios. All right, so let's look at next our rules for ray tracing. All right, rules for ray tracing. All right, number one, a ray entering a converging lens parallel to its axis passes through the focal point, capital F, on the other side of the lens, on the other side. We saw examples of that. That's how you find the focal point. You allow a parallel ray to enter, and where does it converge? That's your focal point. Number two. Number two says a ray entering a diverging lens parallel to its axis seems to come from the focal point F on the same side. Again, its focal point is defined as negative, or focal length is negative for a diverging lens. All right, that's number two. Number three, a ray passing through the center, a ray passing through the center of a converging or a diverging lens does not change direction, unaffected. Okay, four. Number four is a ray entering a converging lens through its focal point. Exits parallel to its axis. Again, when I do some examples, this will become much more clear. Five, and the final. Right, space here. Getting close. A ray that enters a diverging lens by heading toward the focal point on the opposite side, close here, exits parallel to the axis. So let's fit this right here. Barely. Okay, so 5 rules for ray tracing. Number 1, a ray entering a converging lens parallel to its axis passes through the focal point, capital F on the other side. Okay, we saw examples of that already. Ray entering a diverging lens parallel to its axis seems to come from the focal point, capital F on the same side. We saw pictures of that as well. A ray passing through the center of a converging lens or a diverging lens does not change direction. So if you pass through the center, the direction does not change. A ray entering a converging lens through the focal point exits parallel to the surface of its parallel to its axis. Again, if you have a ray that's entering a focal point on the light side or the same side, it'll go out parallel to the axis. Again, we'll show you examples of that. And a ray that enters a diverging lens by heading toward the focal point on the opposite side exits parallel to the axis. Okay, these are going to be rules, and again, this will become more apparent as I do some examples. So let me give you an example of a converging lens. All right, and so I'm going to, as I do this, again, this is, I'm really looking at figure 25.33 from OpenStax, but as I do this, I'm also going to define some other terminology here for ray tracing and lenses. Okay, so we're going to find images on lenses. So let's erase this. Let's apply these rules for ray tracing. All right, well, we have 5 rules. We're going to apply them in order to be able to find images. All right, so I'm going to look at a converging lens where I'm going to say that I'm looking at taking the image of an object that I'm placing further away from the lens than the focal length. So what do I mean by that? So again, this is I'm looking at, if you really want to kind of see what I'm, the better looking image or better looking drawing, look at OpenStax figure 25.33. Take a look at that if you don't like what I'm drawing, but I draw stick figures, but it doesn't matter. All right, so kind of look at that. What I'm doing here is I'm going to draw a converging lens. And again, I'm kind of making it pretty fat there. It's some really more for kind of exaggerated. I'm going to draw an axis through the center. That's called the lens axis. Now, the focal length, I'm going to find the focal length. Again, if the lens, generally speaking, when we write lenses, they're going to be symmetrical, at least in this class. So I'm going to imagine that there's a focal point on either side. They're the same distance away. Okay. Again, this is a converging lens. Again, this is a convex converging lens. Now, I'm going to imagine that I have an object, say a person. And this person is located further away from the lens than the focal length. Again, this is the focal length of this lens. And I'm going to find some terminology here. So I'm going to say that this person is a distance d sub O from the lens. D sub O from the center lens. D sub O is what I'm going to refer to as the object distance. Okay. Now, I'm going to try to figure out where the image is. So I'm going to employ some ray tracing. Again, I'm also going to give you a few other little things here that I'm going to refer to H sub O as a height of the object. Or call it object height. Again, I have an object, I'm trying to find its image. Well, I'm going to employ the ray tracing rules. So what's one rule say? Well, let's look at rule number 1. Rule number 1 says that I'm going to consider parallel light. I'm going to look at the top of this person's head. Let me try to draw this section. My lens is a little bit nicer here. I'm going to trace the top of this person's head. All right. So I'm going to employ my 3 rules. I'm going to employ rule number 1. Rule number 1 means, again, there's an infinite number of rays of light coming from this person's head. And I want to try to figure out where these rays focus on the image. But I don't have to take an infinite number of rays. I just have to take a few rays that are good. So I'm going to pick a parallel ray. One of these lights out of the infinity of rays will actually approach the lens parallel to the axis. And I'm employing rule number 1. What does rule number 1 tell us what's going to happen? Oh, rule number 1 says if you have a parallel light coming from an object, it's going to refract so that it goes through the focal point. Okay. Well, focal point on the other side, it means I'm going to draw it. It's going to refract through the focal point like that. Great. That's one of my rays. That's what happens to the ray from the top of this person's head. It's going to go parallel to the axis and refract such that it goes to the focal point on the other side. That's rule number 1. What about rule number 2? Or let's look at rule number 2. Ray number 1. So again, I'm gonna apply another rule that says, remember this rule that said that rays that go through the center lens nothing happens to them. They do not get refracted. Nothing happens, right? So they go undeflected. So this is going to be a challenge to my drawing skills. All right, so that happened. Okay, this is a bad drawing. Hang on one sec. Let me start this over again. This is not going to work. All right. All right. So make a large lens to account for my not so good drawing skills. All right, here we go again. Here's the axis again. And what I want to consider is, well, I have a focal length in each side, or focal point in each side. And I have a person. Could be anything, could be a figurine, could be a soda can, could be whatever you want. Now, I know that there is this person, there's an object distance I just got them to find. D sub O. This is from the object to the center of, again, that's the center of this lens. D sub O is called the object distance. H sub O is what we refer to as the object height. These are O's here for object. Object height. Okay. Now let me employ my rules again. So again, I have one rule that says take a parallel ray of light. And where does it refract? It refracts through the focal length on the other side, or focal point on the other side. That's one ray of light. I'm tracing rays. I don't want to trace an infinite number of rays. I just want to trace a few rays, enough to figure out where does the top of the head of this person's head form on the image. Well, of all the rays coming from the top of this person's head, one of them will be parallel to the axis. I'll pick that ray. I have another ray. I need to pick one that's going to go through the focal point on the same side, and it will then come out parallel to the axis. That was one of my rules. Pick a ray that goes through the focal length on one side, hits, and it exits parallel to the axis. So that would be so if I look at my rules, this is rule number 1 out of my rules I'm employing, and this is rule number 4. So I'm employing rule number 4. It says that a ray of light going through the focal point exits parallel to the axis. And then one other rule. Now again, I actually could stop right here and figure out where it is, but let's employ one more rule, and that is that the ray that goes through the center of the lens is undeflected. Here we go. Not easy for me. There you go. And that would be what? That would be rule number 3. And notice that in employing these rules, even though there are an infinite number of rays coming from the top of this person's head, I will find out that as I trace these rays, there will be one ray that's going to come parallel from the top of this person's head and hit the lens and will go through the focal length on the other side, or focal point on the other side. One ray will literally go from the top of this person's head through the center of the lens and be undeflected. And another ray would go from the top of this person's head through the focal point on the same side and come out parallel to the axis. Where these rays converge is where this person's image, the top of the head, is going to be. So, and if I want to go and look at another place, like let's say right where the two arms meet at the neck, I can play same ray tracing, and I can get another point. I can do this for every single point on this person's body, or figurine, or whatever it is that I'm looking at. And I'll find out that when I trace this out, the image will be an upside down image. So the image will essentially be upside down, inverted on the other side of the lens. It'll be real because every single ray of light is actually getting there. It'll be a real image. I could put a piece of film. I could put film. I could put a screen. I will see the image appear on that screen. It'll be upside down, be inverted, inverted real image. Now, the distance from the center of the lens to where this image forms is called the image distance. So d sub I is called the image distance. And I can define how tall this image is. Again, it's a length from the axis, and this would be h sub I. H sub I is the image height. These are typically in centimeters, maybe meters, maybe millimeters, depending. Right now, there's a nomenclature here, and that is if d sub I So d sub I is positive on the opposite side. Well, actually remember we refer to the opposite side of the lens as the real side. And the other side of the lens where the object is, that's called the virtual side. All right. So if d sub I is positive on real side, now it turns out I may form an image on the same side, and I'll show you how I can do that. If that's the case, then d sub I is negative on virtual side. Again, for a lens, the real side is the opposite side of the lens. Why? Because that's what light's supposed to do with a lens. The purpose of a lens is to transmit light, to make an image. So if light actually is forming an image on the opposite side of the lens, well, that's exactly where rays of light actually do go. Rays of light actually go through the lens, irrespective of what kind of lens you're talking about. Rays of light go through the lens, transmit through the lens, and if they form an image on the opposite side, that's a real image. We would say that d sub I is positive in that case, in this nomenclature. If, on the other hand, I have, let's say, I'll give you another example where we can actually use a converging lens and get we can actually get an image on the same side. We'll find out that we have an example where d sub I will be on the same side as the object. That would make it a negative d sub I. And then we have a nomenclature for h sub O and h sub I. So h sub O, so if h sub O is right side up, then it is positive. I'll write this better in a minute. If h, I'm sorry, h, not h sub O, h sub I, h sub I, sorry, h sub I. If h sub I is right side up and is positive, if h sub I is upside down, it is negative. So in this particular case, what is my image? My image is real because it's on the real side. D sub I would be positive. My image is inverted. H sub I is negative in this case. It's upside down. My image, if I have an image, if I take an image, if I put an object at a distance from a converging lens further from the focal point, at a distance greater than the focal length, the image will be inverted and real. Okay, now what have I defined here? I defined some very important parameters here for lenses. I've defined the object distance, the image distance, the object height, and the image height. Now, I'm going to show you a set of lens equations. I am not going to prove them. To prove them would just be a bunch of geometry. There really wouldn't be any physics involved. There are places where you can go look up the proofs of them if you so desire. It's all just purely geometrical proof, and I think it'd be, quite honestly, a waste of your time. I do proofs to teach you more physics. This would be just pure geometry proofs. But I mean, if you so desire, that's fine. But these images, I mean, these particular variables are always related. Okay, so again, remember here, I have, in this particular case, I have d sub O is greater than f, greater than the focal length. Okay, so image is real and inverted. You can see it with the ray tracing. What did I do? I could trace an infinite number of rays, right? But you really only want to trace certain ones, and you follow the ray trace rules. You have one rule that says, well, of all the different rays coming off the top of this person's head, one ray is you have a ray parallel to the axis that gets refracted such that it goes through the center of the focal point on the other side. Another rule says that a ray that goes through the center of the lens gets undeflected. And another rule says that a ray that goes through the focal point in the same side comes out of the lens parallel to the axis. Where those rays converge is where you put the top of this person's head in the image. And then you'll left eye, pupil, same kind of thing, belt buckle, right pinky finger. I mean, whatever it is that you want to do, you do point by point by point by point, and you essentially can trace. You can essentially trace out the image of this person's image on the other side. Every single point on the image of whatever it is whatever is the object that you're trying to traces like this. Every single point. I'm just picking one point, the top of this person's head. Now, I gave you a bunch of variables. Now let's show you how they relate. So we have the lens equations. I am not going to prove them. I'm just going to give them to you. Again, I could prove them, but I wouldn't even prove them for my university of physics class. It's just nothing but pure geometry. And I don't think it's going to enrich your understanding of physics. So we have these, what we call the thin lens equations. That's what we call them. And I've defined everything in that previous picture. And we have 1 over d sub o plus 1 over d sub I is 1 over f. D sub o is the object distance, d sub I is the image distance, f is the focal length. Remember, f for a convex lens is positive, f for a concave lens is negative. Again, convex lens is converging, concave lens is diverging. So again, there is a sign that you need to remember for f, depending upon what kind of lens you're talking about, what kind of lens are you dealing with. We'll see more examples of this. We also have the following equation. We have h sub I, the height of the image divided by the height of the object, also equal, so we're going to find what's called magnification. Let's do it this way. Magnification is how much bigger or smaller an object gets, how it magnifies. So this little m here is called its magnification. It's probably easier to understand as the image height divided by the object height. How much bigger is the image than the object? May not necessarily be so obvious to you, but it's also equal to negative image distance over object distance. Again, these equations would be proven through geometry. Magnification is a unitless number. Why? You have height over height, distance over distance. They're going to cancel out. Now, the thing to keep in mind here, if m is greater than 0, I'm sorry, if m is positive, image is upright. If m is negative, image is inverted, upside down. Okay? If the absolute value of m is less than 1, image is reduced in size. If the absolute value of m equals 1, image is same size as object. And if the absolute value of m is greater than 1, then the image is larger, it's magnified than the object. It's called magnification. So these are the two thin lens equations. Again, I have not proven them, and I will not, and I would not prove them for my university physics class either if I taught one. All right. Essentially, it's nothing but ray geometry. 1 over d sub o plus 1 over d sub I equals 1 over f. M is h sub I over h sub o, or negative d sub I over d sub o. Okay, those are the equations. Let's get an example of what more or less what we just got done doing. So we're talking about a case where d sub o is greater than f. Let's do some ray tracing, and let's back it up with some mathematics. Okay, so again, I just got done giving you such an example. So we're going to look at basically OpenStack's example 25.6. All right, OpenStack's example 25.6. All right. What this says is a clear glass light bulb is placed 0.750 meters from a convex lens. Having a 0.500 meter focal length. Okay, very important information here. Use ray tracing to get an approximate location for the image. And then use the thin lens equations to calculate A, the location of the image as d sub I, and B, its magnification verify that ray tracing and the thin lens equation produces consistent results. Okay, so again, no, to me that's apparent. So a clear glass light bulb. So that's our object. We want to image it. It's placed 0.750 meters from a convex lens having a 0.500 meter focal length. And again, that's really what we just got done doing. We're having an object distance greater than the focal length for a convex lens. Okay. Use ray tracing to get an approximate location for the image, then use the thin lens equation to calculate A, the location of the image, that's d sub I, and this magnification M. All right. Now, there'll be some problems that you'll get in this in Cutnell Johnson. It's going to ask you. It's not going to be very many of these problems, but it's going to ask you to use ray tracing to get an answer. You want to get out a ruler. You want to get out, some sort of a way of, kind of like you did when you had the vectors lab, and anybody took me back in physics 1. You want to have some sort of a conversion of, what one length means in a ruler. You want to have a consistent way of actually tracing the distances and finding out where the image is. You don't want to just slop, some lines on a piece of paper. You want to try to do a good job and see that ray tracing actually does work. I can't really do that here, but again, on your paper, when you do one of these kind of examples, you want to make sure you do a very accurate job. All right, so that's really important here. You're literally going to come up with an answer in some of these problems, not using mathematics, but using ray tracing. All right, so I'm going to make that a clear point. All right, so let's do this. First of all, I can't do the nice, beautiful example, with a ruler and stuff. But let's kind of do. I'm going to do the best I can here. So again, part A. So what we want to do is we want to take a look and see. Okay, well, what do we expect to see? Okay, so we have a converging lens. It's fatter in the middle than it is at the ends. Here's my axis. I have a focal point on each side. And I have some sort of an object. I guess it's a light bulb. Something like that, right? I have a light bulb. And I want to try to see what it looks like. So I'm going to look at the top of the light bulb. Now let me try to make my light bulb a little further away. So I'll make my little light bulb. And I really want to image the top of the light bulb. So what am I going to do? Well, I really only need 2 rays. I mean, I showed you 3 rays. It only takes 2 rays to make an image. But let's just say, let's do my parallel ray. That's usually my favorite. And that goes through the focal length on the other side. Okay, that's that ray. Again, I'm tracing, there's an infinite number of rays I can trace off of anything. I'm looking at the top of the light bulb. And let's pick one, let's say through the focal point on this side, on the same side. Now, draw this a little further. Okay. And it comes out parallel. And if I were to draw a 3rd ray, it would cross here as well. So as you're seeing, this is one example of top of light bulb. So again, my light bulb would be, the image of it will look like this. So what do I expect to see? Well, I expect to see d sub I positive. I expect to also see that M, the absolute value M, I expect that to be greater than 1. But I also expect M to be negative. So d sub I positive would mean you have a real image. You're going to form an image on the opposite side. So I expect d sub I to be positive. I also expect it to be greater than F. F being the focal length, little f. So what do I expect for my image? Just for my ray tracing diagrams. Again, I can put a 3rd ray here. I only need 2, right? I expect d sub I to be positive. Positive d sub I means it's on the real side. Remember, there's 2 sides. This is the real side. That's where light really does go. And the virtual, any image form on the virtual side, light does not actually go there. A virtual image would actually appear to come from the same on the virtual side. The real side of a lens is where light rays actually do go. So I expect d sub I to be positive. I also expect d sub I to be greater than the focal length. I also expect the image to actually be magnified. So I expect the absolute value of the magnification to be greater than 1. I also expect the magnification itself to be negative. I expect the image to be inverted. Okay, these are all my expectations to see if they're true. How do I get there? Well, I get there through the mathematics. All right, so what do I know? Well, I'm given some information. I'm given it the object distance. The object distance, I'm told, is 0.750 meters. The image distance, I don't know. I need to find that. And I'm also given a focal length. The focal length of this lens is 0.500 meters. I'm given this information. I use the thin lens equation to determine what d sub I is. So again, 1 over d sub O plus 1 over d sub I is 1 over f. 1 over d sub I is 1 over f minus 1 over d sub O. Plugging in my values, that's good enough. I can just put the numbers in and invert it at this point. So I have 1 over, again, it's a convex lens. So I probably should be a little more careful and tell you that that's actually positive 0.500 meters. Remember, it's a convex lens, so it's positive. All right, so here we go. 1 over 0.500 meters minus 1 over 0.750 meters. When I do the subtraction, I flip it. I find out that d sub I is going to equal 1.50 meters. Well, there you go. It's positive. Positive means that it is on the real side, and as I said, it's further from the focal length than it's further from the lens than the focal length. I expect it to be greater than 0.75, and it is. It's twice it. So d sub I is pretty much what I thought it would be. D sub I is a positive 1.50 meters. That means it's on the real side. Positive means it's real. I'm actually going to get an image there. Light's actually going to go there. Now the question is it magnified? And also, is it inverted? Can I predict that too? All right, well, I use the other thin lens equation. Magnification is negative d sub I over d sub O. And the math is very easy in optics, just that where you can get messed up is getting your signs wrong, right? So negative, or d sub I is a positive number, so 1.50 meters is my d sub I, and my d sub O is 0.750 meters. That's how far away my object was. So my m is going to be basically my m is going to be negative 2.0. Oh, okay. What information can I derive from that? Well, the negative sign tells me it's inverted, and so again, m is negative, which implies an inverted image, means upside down image. The absolute value of m, what's that? That's 2.0, which is greater than 1. That means it's magnified. That means that the image is actually bigger than the object. In fact, it's bigger than the object by a factor of 2. That's exactly what I would expect I would expect to see for this situation. Again, this situation is what? I have a converging lens. The object is further away from the lens than the focal length. So I expect what? I expect a real, inverted, and magnified image every single time. Real, inverted, magnified. All right. Again, in this case, real, image. Here's adjectives for my image. Real, inverted, magnified. All right. Well, what happens if I decide to move my image closer? What happens instead if I decide that I want to, instead of having an object that's actually further from the focal length, what if I want to put it closer than the focal length. What happens now? All right, so let's take a look at another example. And that is, I'm still going to use a converging lens. But now I'm actually going to put the object closer to the focal length. Closer than the focal length to the lens. So again, my previous example was d sub O greater than f with a converging lens. We saw that the image was real, inverted, and magnified. Okay, real, inverted, and magnified. All right, now I want to consider something different now. I want to look at d sub O less than f. I want to move my object so it's closer than the focal length of the lens. All right, so now let's consider d sub O less than f with a converging lens. What happens now? All right, so we'll draw a little picture. Try to, again, an art challenge, so see what I can do here. So draw a converging lens. Here is my axis. Now, I'm going to imagine a focal length in each side. Here's a focal point, here's a focal point. And now I'm going to consider an object that is now closer. Let's maybe draw my little light bulb now, but let's make it closer. All right. So it's going to be closer to, so my d sub I, my d sub O will be here, but it's going to be less than d sub I. And d sub O is the object distance. It's going to be less than, less than f. Object distance is less than f. It's closer. What's going to happen now? Well, what I can do is I can imagine that I have a parallel ray coming from the top of the light bulb, and it's going to go through the focal length on the other side. And I can do that. I really can't draw the ray that goes through the focal length on the same side, but why? Because I'm too close. I'm closer to the lens than the actual focal length. So I can't draw that ray, but I only need two rays. Let's draw the ray that goes through the center of the lens. Draw that ray. So again, the ray that goes through the center of the lens is undeflected. And what I can do now is I can extrapolate. So these rays will actually diverge. What I can do is I can extrapolate back. And I realize, a better job than that. All right, extrapolate back, and I realize that what I actually now get, and let me just draw. What I actually now get is an inverted image. I'm sorry, not inverted, it's a magnified image, but it's right side up. There's my light bulb now. Now your image is actually behind the object, and it is magnified. All right, and so what I expect now is that the image formed is on the same side of the object, or as the object, and it is magnified and upright. And I just employed ray tracing. I mean, I had two rules that I can actually use. I couldn't use the rule where you put the ray through the focal point on the same side. However, I had the parallel ray, which does what? Why? It refracts and goes through the focal point on the other side. And then I have the ray that goes through the center undeflected. I extrapolate these two rays back, and I found the top of the light bulb is actually going to be converge. This is not a very good drawing, but converges to an image that's actually behind the object. So it's going to be a virtual image. So I expect d sub I to be negative. So I expect d sub I negative. I expect m positive. And I expect the absolute value m to be greater than 1. This means that I expect the virtual image, d sub I is negative. I expect m to be positive, which means it's right side up. It is upright. And I expect the absolute value m to be greater than 1, which means it's magnified. All of these I can predict from ray tracing. All right, so let's look at example 25.7. And 25.7 is an example of really a magnifying glass that really brings this to light. No pun intended. All right, so look at example 25.7, which is an example of this. This is example 25.7 from OpenStax. Okay. OpenStax example 25.7. That says, suppose the book page, figure 23.37a, we're not going to worry about that. We'll say, suppose, I'll kind of rewrite it a little differently. A book page is held 7.50 centimeters from a convex lens. Focal length 10.0 centimeters. Again, it's closer than the focal point. Okay. Such as a typical magnifying glass might have. What magnification is produced? All right. This is an exactly like what I just got done saying. I have a focal length f, which is object distance f, which is 7.50 centimeters, a focal length f, which is 10 centimeters, which is when the object distance is actually closer than the focal length, and I want to figure out the magnification. All right, so again, this is exactly like what I just got done showing. All right, so let's remember these and let's work it out. We're gonna work it out with just the mathematics and see if it comes out to be what we expect. So again, what do we expect? Well, we expect a virtual image. So again, we expect, so again, we know that d sub O is 7.50 centimeters. And we know that F is a positive. Again, it's a converging lens, so it's still positive, right? 10.0 centimeters. All right. Now, what do we expect? We expect a negative d sub I, which means virtual. We expect the magnification to be positive, means it's upright. We expect the absolute value of magnification to be greater than 1, which means magnified. Means it's a bigger image. Okay, what do we get? Let's see. Plug it into the thin lens equation. So let's prove this mathematically. So again, thin lens equation, we know that 1 over d sub O plus 1 over d sub I is 1 over F. Solving for d sub I again. 1 over d sub I is 1 over F minus 1 over d sub O. All right, plug in the numbers now and then flip them. 1 over d sub I is 1 over 10 centimeters plus, minus 1 over 7.50 centimeters. And I don't have to worry about converting to meters per se. I do this subtraction and I flip the answer. I get that d sub I is negative 30.0 centimeters. Great. That means that my image is well behind the magnifying glass. All right. So again, and of course that's good for me, right? Because I'm looking at a magnifying glass and my head's way back here, right? So again, I want the image to be in my face, if you will. So again, I do want the image to be projected behind so I can see it. The whole point of magnifying glass is for me to look at some small print and get the image magnified to me, right? So I definitely want something like that. And of course, what else? So it tells me that the image is well behind the object. It's on the same side. And given that it's negative, that means it's virtual. So virtual image means it's on the same side as the object. Now, the other thing that I want to look at here is, let's see, magnification. Magnification is, again, it's going to be negative. Again, be careful with your signs. D sub I over D sub O. That's negative 30 points. Oops, I'm already messing up my signs. Negative, be very careful. Negative of what? Negative of negative. 30.0 centimeters divided by 10 centimeters. Your object, this is always positive. That's going to be positive 3.0. So magnification is positive 3.0. Great. That's exactly what I predicted. Positive means upright. And the absolute value being greater than 1 means it's magnified. All of those things, everything I expect to have happened happens, and mathematics proves it out. All right, we have one other combination to look at here with lenses, and that is the concave lens. What happens now? So now we're going to look at a concave lens or a diverging lens. And see what happens. All right, so concave diverging lens. Sorry, what happens? Well, I have a diverging lens. Try to draw it big. Skinnier in the middle, fatter on the ends. Okay, draw an axis through the center. Here's my axis. Now I have a focal length. Now this time the focal length is negative. Okay, so again, F is negative for concave lens. Concave is again, or diverging, however you want to call it. Concave, remember, is a statement of the shape. All right, now let's take an object. Let's just imagine here I have some sort of an object. I'll just kind of give it by an arrow. All right, maybe it's a pin or something. I have an object, and what's going to happen now? Let me make this a little bit different looking. Make the lens a little taller. Well, I employ the same ray tracing rules. Let's imagine I have parallel ray. What's it going to do? It's going to diverge out. All right, and then I'll employ another one. I'll talk about the ray that goes through, let's say, the center. So again, rays are diverging out. Now, actually, let's draw this a little different. Very good job. Let's say it diverges like this. All right. Now, this is my diverging ray. Now let's imagine where these rays extract back. This ray is going to extract back to a location right here. All right, and so the idea here is that it's going to this is going to be an an object height h sub o. This will have an image height h sub I. This is my d sub o, which is always positive, but my d sub I is only going to be this guy. Right, so my d sub I, my h sub o is, sorry, this is going to be, we'll say h sub I. All right, my d sub I is going to be smaller. It's going to be within the focal length, and it's going to be miniaturized and upright. So the ray trace predicts. Again, I take the diverging rays and I extract back. Where those diverging rays, the extracted rays converge, that is where your image forms. So the ray trace predicts d sub I less d sub I negative, or negative d sub I, i.e. a virtual image on the same side as, again, this is again the real side of the lens. This is the virtual side. So it predicts a negative d sub I, which means virtual image. Okay, it predicts the M negative, or sorry, M positive, so positive M. That means upright. It also predicts that the absolute value of M, however, will be less than 1. This means miniaturized. Not magnified, but made smaller. I expect the image to be upright. I expect it to be smaller. I expect the image to be virtual. For a situation where the a concave lens is used, a diverging lens. Well, let's take a look at OpenStack's example 25.8 and see if that's true. All right. So again, remember these, what we just got done saying here. And let's look at OpenStack's example 25.8. See what if the mathematics backs up the ray tracing. So OpenStack's example 25.8. Let's see. That says, suppose an object such as a book page is held 7.50 centimeters from a concave lens. And just like we just looked at. Focal length, and be careful here. Concave, so we gotta make sure it's negative 10.0 centimeters. Remember, focal lengths for concave diverging lenses are negative. Do not mess up your sign. Such a lens could be used in eyeglasses. To correct pronounced nearsightedness. What magnification is produced? All right, so suppose an object such as a book page is held 7.50 centimeters from a concave lens of length negative 10, focal length. So again, suppose an object such as a book page is held 7.50 centimeters from a concave lens of focal length negative 10.0 centimeters. Such a lens could be used in eyeglasses to correct pronounced nearsightedness. What magnification is produced? Okay, we're going to see if everything we talked about earlier is actually true. You know, what we said on the ray trace. So we're going to back it up with the mathematics. So we have a concave lens example. Let me erase this and I'll, for real estate purposes. So again, looking at OpenStack's example 25.8. So what do we know? Well, we know that the object distance, in this case, we're thinking object distance actually, again, it's actually less than the focal length, but that's fine. 7.50 centimeters. Doesn't really matter for concave lens. You're always going to have the situation. F is negative 10.0 centimeters. Okay, the mathematics, thin lens equation. 1 over d sub O plus 1 over d sub I equals 1 over F every single time. Solving for d sub I, 1 over d sub I is 1 over F minus 1 over d sub O. I could go further and solve for d sub I, but I mean, we can just put the numbers in now and flip them. 1 over d sub I is 1 over F. Okay, be careful. Is 1 over negative 10.0 centimeters. Minus, this is an algebraic minus, 1 over 7.50 centimeters. So basically, it's going to be the addition of two negatives. What you'll get when you do this, you do this calculation, flip the answer. you'll have that d sub I is negative 4.29 centimeters. So again, the image distance is going to be within the focal length, just like I stated, I showed in the last example. I gave an example where the actual focal length was actually greater than the deal was greater than the focal length, but actually this works just as well if d sub O is within the focal length, like in this case. Well, let's take a look at the magnification. What do we expect? Again, I mean, this says virtual image. Why? Because it's negative. So again, it's on the same side as the object. It is virtual. Light rays are supposed to go to the other side. So images formed on the same side of the object are considered virtual images. All right. What about the magnification? I predict it will be upright and miniaturized. Let's see if that's the case. So magnification is negative d sub I over d sub O. Let's see. It's negative 4.29 centimeters divided by d sub O, which was 7.50 centimeters. I get that M is 0.572. All right, it's positive, which means upright image. The absolute value of M is less than 1. That means it's miniaturized. Made smaller. All right. So putting everything together for thin lenses, what did we just find out? We make a little table here. In fact, I'm just going to copy table 25.3. In fact, I'll just show you table 25.3. Let me go back to the book and I'll show you the table 25.3, which in OpenStax just pretty much sums up together what we just got done saying. Let me go to that spot in OpenStax real quick. Give me a moment. All right, so putting it all together, this table sums it up nicely once I finally get to the table. All right, it's coming. All right, summing everything up here. A lot of pages here. Still parsing OpenStax. Here we go. Here's the table I want. Let me share my screen. All right, so the table that I'm about to show you is pretty much summarizes everything about thin lenses. Okay, you have 3 cases that I've showed you. The first case was the first 2 cases are you're talking about a converging lens where F is positive. The focal length of the converging lens is positive. So case 1 and case 2 discuss converging lenses. The first case was the object distance was greater than the focal length. Okay, so in that case, the image was real. The d sub I, of course, is positive, and the image is inverted. The M is negative. And in fact, we found that the M was actually magnified. Okay. Case 2, we looked at again a converging lens, but this time d sub O was actually less than F. In that case, we found that the image was virtual. It was actually behind the object, like a magnifying glass. D sub I, of course, was negative. That means virtual. D sub I positive means real for lenses. D sub I negative means virtual. We found that the M was in this case was positive, which means upright. So again, In the first case, it was inverted. M was inverted in the first case. That means that it was upside down. M was positive or upright in the second case. And again, the absolute value of M is greater than 1, which means it's magnified as well. So again, case 1 and case 2, both are cases where the F, the focal length of the lens, is positive, which means, again, that the lens is converging. It is a convex lens. It's a converging lens. Okay, and we define F as positive for that situation. If I consider an object distance greater than the focal length, like in the case 1, the image on the other side will be real. Real means it's on the other side. That means d sub I is on the positive side of the real side. So d sub I will, of course, be positive. But the M will be negative, which means it means that the image will be inverted. In case 2, we still have the same converging lens, but now we consider the object distance less than the focal length. In that particular case, the image will be formed behind the object. So then d sub I will be negative, which means it will be virtual. Image distance will be negative. It's on the object side. It's on the virtual side. And the M, the magnification, will be positive, and it'll be greater than 1, which means it'll be positive, and the image will be magnified. Case 3 was a case where F was negative. That was a case of a concave lens. We found that the image for a concave lens was, again, the d sub I is negative, and the image is always virtual. And the image is always upright, so M is positive, but M is miniaturized. The absolute value of M is less than 1. It's miniaturized. All right, so that's the case for lenses. Now we go into the case for mirrors. All right, so we talk about mirrors now. So here we have lenses. Now, again, lenses is an application of the law of refraction. Mirrors is the application of the law of reflection. So the next topic we're going to talk about is mirrors. Okay. So going back, lenses what happened there? This thing got moved. All right. Lenses is an application of the law of refraction. Or Snell's law. Which again is N1 sine theta 1 is N2 sine theta 2. Mirrors, a mirror, actually lenses are an application. Or, well, a lens is an application. A mirror is an application of the law of reflection. Or Hero's law. And that just says that, again, N1 sine, should be more clear here, N1 sine of theta incident is N2 sine of theta transmitted, right? Here, Hero's law is that the angle of incidence equals the angle of reflection. I mean, that's all the mathematics that goes on in mirrors. The angle of incidence equals the angle of reflection. All right, and so again, you know, you only have to go to your nearest bathroom to see a mirror. And so you normally will see a mirror that's like a plane mirror. Just kind of take a look at what that looks like. Give me an example here of a plane mirror. All right, here's a good example of a mirror. Share my screen. All right, what you see in a mirror is we're looking at like a little bottle. A bottle, again, this is a plain mirror, flat mirror, as it says. The bottle has an object distance d sub o. Now, we take a couple of rays from the bottom of the bottle and a couple of rays from the top of the bottle. And you notice how they both will strike the mirror. The angle of incidence equals the angle of reflection. Both of those rays make it into the eye. You see a picture of the eyeball, up around here. Both of those rays enter the eye. Now, the actual image, though, would form if you take those rays, those reflected rays, and extrapolate them back behind the mirror. And when you do so, you notice that there is the image that forms. It looks exactly like the bottle, looks exactly like the object, except and it's actually behind the mirror, as far behind the mirror as it is in front of the mirror. So the object actually forms behind the mirror. We refer to that as a virtual image. So it's the exact opposite of what you see with lenses. So again, you see this concept of images. The image, we refer this to a virtual image. The actual image appears behind the mirror. If you were to go behind the mirror itself, you would see no light there. All right, and so the actual image is behind the mirror. It is exactly as if the mirror wasn't there, and the object, you put the bottle right exactly where you see the image. You'd see the exact same view. All right, and so in this particular case, now that's the flat mirror, and now what we can say here is, what we want to actually do is take a look at a little bit more complicated mirrors. So we're going to look at a situation where we actually look at a curved mirror. So I want to take a look at a curved mirror, and again, this is called this is actually called a concave mirror. All right, it is concave because of its shape. Now let's see what happens with light rays. Light rays come parallel. Again, this is the light's coming from the left to a concave mirror. Why is it concave? Because again, it has to deal with the shape. If I were to continue drawing that circle, the light rays would be within the circle. The radius of curvature is on the same side of the circle as the object. Again, their light rays are coming from within the circle that this mirror would be a part of. This is a concave mirror. Now, unlike lenses, real images formed on the opposite side of a lens. Why? Because that's what light is supposed to do. It's supposed to go through a lens. The purpose of a lens is to exercise Snell's law, or the law of refraction. The purpose of a mirror is to exercise the law of reflection. Light actually stays on the same side of the mirror. So real images are actually formed on the same side of the mirror, which is the exact opposite convention as lenses. Real images are always on the opposite side of the lens, but real images are on the same side as the mirror. Now, notice something interesting here. If you look at picture A, the picture is showing you that there is a blurring of the image. right? The image looks like it is blurred. All right, and so what we want to do is well, and this is a problem with spherical mirrors, is that the actual rays do not converge to a point. What we actually have to do is make an approximation, and that is the approximation is that the size of the mirror is small compared to the radius of curvature. That gets you to the rightmost picture. When you make the approximation, and I'll write this down on the whiteboard in a moment. When you make the approximation that the size of the mirror is small compared with this radius of curvature, then the reflected rays of light will converge at the image, at the focal length. Again, what you're seeing here is you're seeing parallel rays of light. Parallel rays of light on the right-hand side are converging to a focal length, or at a focal point, at a focal length given by little f, as you see in the picture. If you do not make that approximation, the parallel rays of light will actually form a blurred image, and they will not converge to the same point. All right. So to get to converge to the same point, you have to make an approximation that the size of the mirror is small compared with the radius of curvature. This is basically the mirror's equivalent of the thin lens approximation. So let me kind of write this down here. So what I showed you in the second picture is in the second picture, we're showing what's called a concave mirror. All right, concave mirror. Okay. Now, what a concave mirror does, well, first of all, concave again is a statement of shape. It means that the light rays, if I were to continue drawing the circle, this circle would be part of a circle when the radius of curvature is part of the circle. This would be the radius of curvature. So parallel rays of light all perform the angle of incidence equals angle of reflection and converge to a single point. Any given parallel ray of light will do the same thing. So on and so forth. They all converge to some focal point F. Focal point is where the rays of light converge. This is considered a focal length. So for a mirror, the left side is the real side, and the opposite side is the virtual side. Why? Because for a mirror, light is supposed to be reflected. For a mirror, it gets reflected on the same side as a mirror, whereas light's not supposed to go through the mirror. So if you see an image formed behind the mirror, that's called a virtual image for a mirror. It's the exact opposite nomenclature, exact opposite convention as you saw for lenses. All right. So a concave mirror is a converging mirror. It converges light. A concave mirror is a converging mirror. All right, concave mirror is a converging mirror. On the other side, and again, it's the left side is considered real, the other side is virtual. What happens if, I have another example here. And oh, one more thing is, we form an approximation to get rays of light to focus at focal point F, the size of the mirror must be much less than its radius of curvature. Okay, this is the mirror's, this is the mirror's equivalent, if you will, of the thin lens approximation that we talked about earlier. All right, so that's if you're to get a nice clear focus. To really do a perfect job, you'd want to have a parabolic mirror. But parabolic mirrors are expensive. So again, these are spherical mirrors. All right. So again, to do a perfect job, you'd want a parabolic mirror. All right. So again, to get a perfect focus no matter what, we would use parabolic mirrors. But those are too expensive to manufacture. So we use spherical mirrors whose size is much less than the radius of curvature. All right, so we have to make it, you know, for economical purposes, we have to use spherical mirrors and use this approximation. I believe the Hubble telescope may have parabolic mirrors, but again, parabolic mirrors are very expensive to make. And so you're much, you know, generally speaking, you're gonna in your life, you're gonna see spherical mirrors that have this approximation because they're cheaper. Okay, now we could go and look at okay, issue my alignment here of my whiteboard. Okay, let's take a look at the book again. And I'm going to show you an example of a convex mirror. And share my screen. Okay. What you see now is a convex mirror. Again, convex is a shape, and again, the shape bows outward toward where the light is coming from, the parallel light, and the circle, if you're considered continue drawing a circle, you'd always be, no matter what, you'd always be outside of that circle. Now, the mirror is on the left-hand side. So what it's going to do, again, it's going to do angle of, it's going to do Hero's law, or angle of incidence equals angle of reflection for every single ray of light. And the rays, of course, will diverge on the object side of the mirror, the real side, the object side of the mirror. If you were to extrapolate those rays backwards, they would appear to be the image would appear to be behind the mirror, or on the virtual or negative side of the mirror. Again, this is you'd be forming an image on the back of the mirror. That would be the virtual side of the mirror. Light does not actually go there, but that would be where the image would form. We just saw that as an example. Well, plane mirror. Again, the image forms on the behind the mirror, the virtual side of the mirror. So for a convex mirror, the actual image is on the focal point would be on the back of the mirror. That focal length for a convex mirror or a diverging mirror is negative. All right, the focal length for a concave mirror or a converging mirror is positive. All right, so let's kind of, we can kind of compare and contrast. So let me go back to the whiteboard here and draw the little picture. So what I now have is a situation where I now have a convex mirror. Again, convex is nothing but a statement of geometry. It's a statement of shape. All right, so a statement of shape essentially means that now, again, this is a convex or diverging mirror. All right, so now the shape is such that it bows out toward the light. So light comes in, here's the axis. Well, parallel rays come in. And again, what do? They angle of incidence equals angle of reflection, so they reflect back. That's where the rays actually go. Maybe take a couple more parallel rays to come in. And they should, again, I'm not doing a very good job here, but you get the idea. They extrapolate back to a focus. And my drawing's not very good, but that's the whole point is F in this particular case is negative. So F is negative. It's defined as negative. Focal length is defined as negative for a concave diverging mirror. Okay, so let's kind of compare and contrast here lenses and mirrors really quickly. This is probably, it can be a little bit confusing probably. So we know that for a lens, lenses compared with mirrors, so a convex lens is converging. So a convex lens converges light, whereas a convex mirror is diverging. So remember, convex or concave deal with the shape of the surfaces. Converging or diverging deal with what happens to the light. So a convex lens converges light. A convex mirror diverges light. A concave lens is diverging, whereas a concave mirror is converging. For a lens, the real side is opposite side of lens. For a mirror, the real side is the same side. For a lens, the virtual side is the same side. For a mirror, virtual side is opposite side, behind the mirror. Now, it turns out that the same equations apply. Again, I'm not doing the proofs here, but it turns out the thin lens equations apply to both. For both, I can write 1 over d sub O plus 1 over d sub I equals 1 over f. And I can write the magnification is h sub I over h sub O, which is negative d sub I over d sub O. Okay, now this is different now. So again, for a remember, for a converging lens, we have f greater than 0, positive. For a diverging lens, f is less than 0. For a diverging or a convex mirror, again, it's diverging, so f would be defined as to be negative. If a concave mirror is converging, f would be defined as positive. So f, occurring on the same side of a mirror is positive. F occurring on the same side of a lens is negative. F occurring on the opposite side of a mirror is negative. F occurring on the opposite side of a lens is positive. Again, the idea is that light is supposed to go through a lens, so a real image would form on the opposite side of the lens. Light is supposed to be reflected off of a mirror, so a real image would be in the same side of a mirror. And that's really what it gets down to. Now, there's one other equation regarding mirrors, and I'm also going to state this without proof as well. For a mirror, you actually do have a nice equation here that there's a relationship that the focal length, again, this is just for a mirror, is the radius of curvature divided by 2. Again, that's only for a mirror, and I'm not going to prove that. The other thing that applies to both is that the power is 1 over the focal length. And that's the case for both of them. So I'm trying to, all right. So at this point, now we'd like to actually talk about the rules for ray tracing again for mirrors. At this point, I'll go through some problems. So there's rules for ray tracing for mirrors as well. Again, you want to ray trace. And if you get problems that deal with ray tracing, again, you're going to want to get out your ruler and very carefully measure. You don't want to draw some sloppy pictures. You want to actually, carefully measure. And so we have rules for ray tracing for mirrors. All right, 5 rules, just like before. Rule number 1. A ray approaching a concave converging mirror is reflected through the focal point F of the mirror on the same side. You saw a picture of that. All right, number 2. Array approaching a convex diverging mirror. Parallel to its axis. Hang on, I didn't write this right. Hang on. Back up, back up. I didn't write rule number 1 correctly. All right, rule number 1 again. It says, array approaching a concave converging mirror. Parallel to its axis. It is reflected through the focal point F of the mirror on the same side. We saw a picture of that in the OpenStax book. Number 2, array approaching a convex diverging mirror. Parallel to its axis. Is reflected so that it seems to come from the focal point F behind the mirror. Number 3, any ray striking the center of a mirror is followed by applying the law of reflection. And that's all right. So again, that's just for the center of the mirror, irrespective of whether it's converging or diverging. Number 4, array approaching a concave converging mirror through its focal point. is reflected parallel to its axis. What do I have? All right, so I can fit number 5. 5. Let's see. A ray approaching a convex diverging mirror by heading toward its focal point on the opposite side. Is reflected parallel to the axis. I've run out of room. So sorry about that. Reflected parallel to axis. Try to fit this. All right. Sorry about this. All right. So number 1, a ray approaching a concave converging mirror parallel to its axis reflected through the focal point F, capital F of the mirror on the same side. We saw a picture of that in the book. A ray approaching a convex diverging mirror parallel to its axis reflected so that it seems to come from the focal point cap F behind the mirror. Number 3, any ray striking the center of a mirror is followed by applying the law of reflection. 4, a ray approaching a concave converging mirror through its focal point on the same side is reflected parallel to its axis. An array approaching a convex diverging mirror by heading toward its focal point on the opposite side is reflected parallel to its axis. Very similar looking rules than you have for lenses, all right? But this is for really applying the law of reflection. The only math going on here is the law of reflection. Angle of incidence equals angle of reflection. It's all that's going on in the operation of mirrors. So that's about as simple the math as you can possibly get. Okay, so now let's look at let me work out some problems here. I'm gonna look at OpenStax 25.36. Get ourselves get some problems with lenses and mirrors. So, well, let me do OpenStax 25.36. I'm going to work lens and mirror problems. All right, we're going to kind of see both of them, right? On the thing. All right, so what is the power in diopters of a camera lens that has a 50.0 millimeter focal length? Okay. So remember, so what do we know? We know the focal length is 50.0 millimeters. But we're talking about power. So we have to put this into meters. All right, and so that's the only time you really have to worry about unit conversions in optics is when you're talking about power. So again, 50.0 millimeters is 0.050 meters. The power is simply 1 divided by f, or 1 divided by 0.050 meters, and that comes out to be 20.0 diopters. The symbol for diopters is capital D. All right, so the power of this lens is 20.0 diopters. All right, look at 25.39, open stacks. $25.39. That says you note your prescription for new eyeglasses. So you note that your prescription for new eyeglasses is negative 4.50 diopters. What will their focal length be? All right, so now we're going to go back into power. So we have power, we're told is negative 4.50 diopters. Or another way of saying that's negative 4.50 inverse meters. And of course, we know the power is 1 over F. Flipping everything upside down, we can simply say that F is going to be negative 1 over 4.50 meters. Or we'll say, flip it upside down, we get that the focal length then is negative 0.222 meters, or negative 22.2 centimeters. You know the power, you get the focal length. Let's look at OpenStax 25.40. All right, what does that say? How far from the lens must the film in a camera be? If the lens has a 35.0 millimeter focal length, back in the day we had 35 millimeter lenses. If the lens has a 35.0 millimeter focal length, remember the 35 millimeter cameras, and is being used to photograph a flower. .0 centimeters away. All right. So, how far from the lens must the film in a camera be? If the lens has a 35.0 millimeter focal length and is being used to photograph a flower 75.0 centimeters away. So what this is really asking is, I need to figure out where, so first of all, my camera has a 35.0 millimeter focal length, right? Again, it's the old, what you call 35 millimeter camera. All right, the object distance is 75 centimeters. And I want to try to figure out, where do I put the film such that the image forms on the film? Okay, that must be done at the image distance. I must put the film at an image distance from the lens such that the image actually forms on the film. So that's what I'm looking for. I'm looking for d sub I. Now I need to get some sort of a set of units that is I mean, I'm mixing units here, so let's put them all in meters, I guess. So in this particular case, well, I can just convert in meters on the fly. All right, so I want to use the thin lens equation. So again, 1 over d sub O is 1 over d sub O plus 1 over d sub I is 1 over F. All right, so I'm looking for 1 over d sub I. 1 over d sub I is 1 over d sub O minus, 1 over F minus 1 over d sub O. Well, that's 1 over, let's get this straight here. So 35 millimeters is 3.50 times 10 to the negative 2 meters. And 75 centimeters, that's minus 1 over 0.750 meters. All right, and so taking this subtraction, flipping the answer, I find out that d sub I must equal 3.67 times 10 to the negative 2 meters, or 36.7 millimeters. That is where the film must be. In order for me, that must be the placement of the film within the camera in order for an image on the film to be formed. Again, this is the old 35 millimeter camera. Nobody uses those anymore. Now we use cell phones, right? But again, that is where the image in the camera would have to be if you in the old 35 millimeter cameras. And 35 millimeter means that's what the focal length of the camera is. All right. Let's do another problem. OpenStax 25.41. This one says a certain slide projector has a 100 millimeter focal length. Lens. A How far away is the screen? If the slide is placed 103 millimeters from the lens. And produces a sharp image. Okay. B says if the slide is 24 by 36 millimeters. What are the dimensions of the image? Okay, so 25.41 says a certain slide projector has a 100 millimeter focal length lens. Okay, that's the focal length. That's F. How far away is the screen? How far away is the screen if the slide is placed 103 millimeters from the lens? Okay, that's your D sub O, and produces a sharp image. That's your D sub I. Then we're going to talk about like if the slide itself is 24 by 36 millimeters, what are the dimensions of the image? All right, so again, there's two parts of this problem. All right, so remember our numbers here. F is 100 millimeters. Okay, D sub O is 103 millimeters. That's where you're putting the slide. D sub I is where the image is going. Again, as usual, you employ the thin lens equation. 1 over D sub O plus 1 over D sub I is 1 over F. Looking for D sub I. So again, I algebraically solve this. 1 over D sub I is 1 over F minus 1 over D sub O. 1 over D sub I will be 1 over, again, I want to try to get everything in the same, well, I can keep them in millimeters, I guess. 1 over 100 millimeters minus D sub O, that's 1 over 103 millimeters. If I do that subtraction and I flip it, I find out that D sub I is going to actually be 3.433 times 10 to the third millimeters, which means that D sub I will be 3.43 meters away. The image will be, far away from the projector as you would want it to be. How much bigger is it going to be? So now I know D sub I. It's 3.43 meters. All right. Now I'm going to figure out how my dimensions expand. Each dimension expands individually. And so I'm going to have my length 1, my L1, for instance, will be 24 millimeters. And my W1, my width 1, as I was given in the problem, is 36 millimeters. What will the length and width of the images be? Well, what you do is you employ the magnification both ways. I have to figure out the magnification first. So again, the magnification is always negative D sub I over D sub O, or negative 3.43 meters. Actually, let's Yeah, 3.43 meters, and that's divided by d sub o, which is 103 millimeters, or 0.103 meters. I find out that the magnification will be negative 33.3. So quite a large magnification. So if I want to find out what the new dimensions will be, I literally just do this. I say, well, L2 with the absolute value of the magnification times L1, or the absolute value of negative 33.3 times 24 millimeters. When I do that, I find out that L2 is 800 millimeters, or 80 centimeters. All right, so this little image, the length of it gets expanded from 24 millimeters to 80 centimeters. What about the width? Well, again, the width W2 will be the absolute value of the magnification times the initial width W1. W2 will be the absolute value of negative 33.3 times 36 millimeters. And I find out that W2, that becomes 1200 millimeters, or 1.20 meters. So again, those are the length, that's the length and width of the actual image. So the small rectangular image is getting expanded into a much larger image. All right, a few more problems to go, and then that'll be it for this particular lecture here. So let me look at OpenStax 25.46. All right. That says, suppose your 50.0 millimeter focal length camera has lens is 51.0 millimeters away from the film. In the camera. How far away is an object that is in focus? So A, how far away is an object that is in focus? And then part B is, what is the height of the object? What is the height of the object? If the image is 2.00 centimeters high. Okay, suppose your 50.0 millimeter focal length camera, that's your F, is 51.0 millimeters away from the film in the camera. That's your D sub I. That's where you place your film to get the image. How far away is an object, that's your D sub O, that is in focus, okay? And so assuming that your 51 millimeters is just the right length to focus the object that's at some D sub O. Then what is the height of the object that the image is 2.0 centimeters high? So again, I have to get the magnification from my D sub O's and D sub I's and apply it the diversion that's a ratio of heights. Okay, so that's the game plan for this problem. All right, so again, another image problem. Again, I'm told what F is. I'm given F is 50 millimeters. I have a 50 millimeter camera here. I'm told that D sub I is a location of the placement of a film with respect to the lens. It's being placed at 51 millimeters. I want to find out how far away an object that's in focus is. That's my D sub O. So again, I applied the thin lens equation, but again, 1 over D sub O plus 1 over D sub I is 1 over F. Solving for D sub O. 1 over D sub O is 1 over F minus 1 over D sub I. 1 over D sub O is 1 over, the focal length is 50.0 millimeters, minus 1 over the object, I'm sorry, the image distance of 51 millimeters. I find out, I do the subtraction, I flip it upside down, I find out that D sub O is going to be 2550 millimeters, which is another way of saying 2.55 meters. That's how far away that object is going to be if I'm focusing it at 51 millimeters inside the camera. That's where I'm placing my film. Now, I want to figure out how high the object is, or how high the object is. I know something else. I know the image height is 2.00 centimeters. All right, so what do I do? Well, I want to find a magnification, but all I know is D sub O and D sub I. So I know there's two forms of the magnification formula. M is negative D sub I over D sub O, but there's also a form that's it's H sub I over H sub O. All right, so what I can actually do is not even have to calculate the magnification. I can just go straight from the relationships of these object image distances to the heights. So I know everything except H sub O. Let's solve this equation for H sub O. So solving for it, I get H sub O is, and I'm going to neglect the negative sign. I have H sub I times D sub over D sub I. All right, and that's going to be, and again, I'm neglecting the negative sign here. All right, so plugging it straight in, I can say, well, H sub O, I have 2 centimeters, and I have a unitless fraction, so I can keep it in centimeters here. So D sub O over D sub I. Let's see, I have 2550, let's see, yeah, 2550 millimeters divided by the original millimeters, D sub I is 51 millimeters. So if I do this calculation, I will find out that H sub O is actually going to be 100 centimeters, which equals 1.00 meters. All right, so again, using the thin lens equation and then using both forms of the equation for magnification. And I don't even have to calculate the magnification directly. I can just relate the two sets of lengths. All right, let me do OpenStax 25.48. That says what magnification will be produced by a lens of power negative 4.00 diopters. And then they have a parenthetical statement, such as might be used to correct myopia or nearsightedness. If an object is held uh, 25.0 centimeters away. Okay, what magnification will be produced by a lens of power negative 4.00 diopters, such as might be used to correct myopia, if an object is held 25.0 centimeters away? So again, I'm looking at the power, P, which is 1 over F, and I also am being told what the basically what the object distance is. All right, so let me erase for real estate purposes. Okay, so I'm being told the power is negative 4.00 diopters. I'm also being told the object distance. D sub O is 25 centimeters. Okay, so I want to find a magnification. So first of all, I know the power is always 1 divided by the focal length. That means that the focal length is 1 divided by the power. The focal length is 1 divided by negative 4.00 diopters. And of course, the answer is going to be in meters, right? And so this will be negative 0.25 meters or 25 centimeters, negative 25 centimeters. Now, I want to find a magnification. And I know, well, there's 2 forms of it, right? It's negative D sub I over D sub O or H sub I over H sub O. Well, the only hope I have is to find the image distance and get the magnification that way. So let's do that. I get the image distance again by using the thin lens formula. 1 over D sub O was 1 over D sub I is 1 over F. This time I want to find D sub I, so 1 over D sub I is 1 over F minus 1 over D sub O. 1 over D sub I is 1 over 25, be careful with your signs. Negative 25 centimeters. If you don't get your signs right, you're going to have a ridiculous answer. Okay, minus 1 over 25 centimeters. I do this difference and I flip the answer. I get that D sub I is going to be negative 12.5 centimeters. Great. Now I can calculate the magnification. The magnification is going to be negative D sub I over D sub O, or negative of negative 12.5 centimeters divided by 25 centimeters. And we find out that the magnification will be positive 0.500. So it's basically upright and half the size. Okay. So again, I got the power. I can get the focal length from that. I was given D sub O. I had to kind of do some chess here to figure out, well, where am I trying to go? Oh, I need D sub I. And I want to get magnification. I need D sub I to get that. So I had to go get D sub I first from the thin lens formula. All right. 2 more problems. OpenStack's 25.55. So we need to talk at least a couple problems on mirrors. Yeah, we're done with lenses right now. Let's get a couple problems on mirrors. OpenStack's 25.55. All right, that one says A, calculate the focal length of the mirror. Formed by the shiny back of a spoon. That has a 3.00 centimeter radius of curvature. B, what is the power in diopters? I guess B. What is the power? In diopters. All right, so what do I know? I know the radius of curvature. Okay, well, the radius of curvature, I can actually get, from the radius of curvature, I actually can get the focal length. Remember, I gave you a formula that I did not prove, but the radius of curvature, you can get the focal length by knowing the radius of curvature, and you divide that by 2. Okay, I know the focal length, I'm given it. Now, again, it is the focal length, we're talking about a convex mirror. All right, so focal length is actually going to be negative. So negative 3.00 centimeters, so we're really talking about a convex mirror. Convex mirror forms virtual images. So I'll get the radius of curvature simply by, I'm given, oops, hold on one second. Hang on a second. Brain's not working here. I'm given the radius of curvature, so the exact opposite. Radius of curvature is 3.00 centimeters. But F is negative. Since we're talking about a convex mirror. Okay, there's a spoon and it curves out toward you. So if I figure out I can figure out the focal length simply by saying, well, that's going to then be negative 3.00 centimeters divided by 2. So quite simply, the focal length is nothing more than negative 1.50 centimeters. That's part A. Part B, I'm going to get the power. Well, B is simply the power is 1 divided by the focal length. I got to get the focal length in terms of meters. I cannot use the power in terms of centimeters. All right, and so in order to do that, I'd have to say that the power is 1 divided by negative 1.50 times 10 to the negative 2 meters. So I find out that the power of this mirror will be negative 66.7 diopters. And all the formulas for lenses also work for mirrors. So that image would then be what? Virtual, which means it's behind the mirror. All right, let's do OpenStack's 25.58. One more mirror problem. That one says a shopper standing 3.00 meters from a convex security mirror sees his image. With a magnification of 0.250. Okay. A, where is his image? B, what is the focal length of the mirror? C, what is its radius or curvature? All right. A shopper standing 3.00 meters, that's your D sub O, from a convex security mirror, convex, okay, means it makes virtual images behind the mirror, sees this image with a magnification of 0.250, okay, that's the magnification. His image is a fourth the size of the object. Where is his image? What is the focal length of the mirror and where is the radius or curvature? Okay, so let's, again, this is more applications of the same equations, but now to mirrors. So looking at part A. Okay, so what I know is the object distance is 3.00 meters. That's where the shopper is standing with respect to the mirror. The magnification, we're told, is 0.250. Again, that's the, and then the image distance, we like to know what that is. Okay, now we look at, again, the magnification we're told is a positive 0.250. So again, what is the magnification? Again, magnification is given, one of the forms of the equations is negative D sub I over D sub O, which means I can solve for D sub I, which is nothing more than M D sub O. So D sub I is going to be, negative, that is, negative M, 0.250. Remember, M is a positive magnification, times D sub O, which is 3.00 meters. D sub I is going to be negative 0.750 meters, or negative 75.0 centimeters. So what does that mean? Well, D sub I is negative 75.0 centimeters, or 75.0 centimeters behind the mirror, where light does not go. It's a virtual image. That's part A. And using just the definition of magnification. But I can use that definition, and now I have D sub I. What B says is, well, okay, what's the focal length of the mirror? Well, the focal length, I can get that now that I know D sub O, and I erased it, of course. D sub O is 3.00 meters, and I'm told the magnification is 0.250, right? Now that I know d sub O and d sub I can actually get F from the thin lens equation. So that's again going to be right here. This one outside the camera. OpenStax 25.58. Thing keeps wanting to rotate. Okay. I don't know why that's happening. It wants to move. Okay. Okay. B, I can use the thin lens equation. 1 over d sub O plus 1 over d sub I is 1 over F. Or flipping the about the equal sign, 1 over F is 1 over d sub O plus 1 over d sub I, or 1 over F is 1 over the object distance, 3.00 meters, minus, plus, be careful now, 1 over the image distance. The image is negative now, so be careful that that's what will screw you up faster than anything else on science, is your science. The math is easy. If you do this, basically a subtraction, if you will, and flip it upside down, you find out that the focal length will be negative 1.00 meters. And you expect it to be negative. Why? Because you're talking about a convex mirror. Convex mirrors make virtual images, so the focal length is defined to be negative. All right, negative 1.0 meter focal length. All right, one more question. I want to find the radius of curvature. Well, remember the radius of curvature is given by a pretty simple formula. I never proved it, but the radius of curvature, what the relationship is that the focal length is the radius of curvature divided by 2. I know the focal length now, right, from part B. So that means that the radius of curvature is 2 times, I'll call it the absolute value of the focal length, because the radius of curvature is really a measurement, a length measurement. So R be 2 times the absolute value of negative 1.00 meters. 2 times 1 is 2. So radius of curvature is just nothing more than 2.00 meters. That's your radius of curvature. That's the answer to part C.